Oh.
Right, says we're live.
Ooh.
Whether you believe it or not, it's another story.
Yeah, well, I'm looking at your...
Right.
Oh, something's happening. Yes. Things are happening, Al. Things are happening. Yes, we've got action.
Hey. Whoa.
Right. Give me a sec. I just need to change the view on OBS.
Right, I'm going to close this goddamn...
And switch to Skype. How's that? Right, I think we're in business, chaps.
I think we are
then.
as well.
Jesus Christ, right.
Yay!
Right, so I will share my introduction and share my screen. Oh my god, right, here
Rumpus,
we go.
Rumpus, turn off autosave.
I have. I did that earlier. Right, hello people, this is courtesy of Al, who stepped in to save my bacon after a somewhat problematic experience with XSplit, doing strange things, interacting with Skype in a rather unpleasant way. And we are here to talk about the Black Swan issue that came up and recently, which is basically this image here. And with me and with Al is obviously Al. We've got Roohif, we've got Big BlueMarbleScience, we've got Dean, Stingray, and George Hnatiuk, and other people.
Hnatiuk.
Hnatiuk. Right, so this is all about this image here, which has been proposed as proof of the flat Earth, and because basically you can see further than the geometric horizon, and because the argument has been given that supposedly globers describe the horizon as the geometric horizon rather than the apparent horizon, and therefore if you can see beyond the apparent horizon, it can't be a globe. So this is with and the Black Swan, White Swan actually was an argument. Quantum Eraser initiated this description of it being the Black Swan, White Swan, but actually he didn't. He initially offered an argument related to this, this using this very same image, and then I explained in a hangout with Jose J.J. Gonzalez to other globers who were not that all that a flatty would need to do if we were making the argument that the horizon that you see is the geometric horizon, then they only need to find one exception, and then that would invalidate the globe. But of course, Quantum Razor puts us in the modus tollens argument, which is basically something like if something is true, if P implies Q, and you have not Q, then you can't have P. It's a basic argument. It's a bit like if P implies Q, you have P, and then you have Q. But similarly, if you have not Q, the result of the consequent, then if you don't have that, you can't have the antecedent. And the antecedent in this case would be the globe Earth. So if the globe Earth exists, then in theory, if the horizon was determined by geometry, therefore you should not be able to see beyond the horizon. But of course, the problem is, and that's called modus tollens, that argument. And the thing is, of course, that no glober ever claims that what we see as a horizon is the geometric horizon. And no matter how many times we say this, because they don't understand what a horizon is, and we'll be discussing this later, they believe that we claim that you see the geometric horizon. But of course, that's only that relevant if you have light that travels in straight lines. The geometric horizon only has meaning if light travels in straight lines, and of course it doesn't. So this image, and we're going to examine way refraction works. We're going to examine how way horizons work, and we're going to do a little bit of image analysis as well. and explain what's going on in this image. And oh yes, I'm sorry. And I then characterised this argument as a Black Swan, White Swan argument, that you only need to find one, which is described by Karl Popper as saying, if you make the claim that all swans are white, you only need to find one black swan to invalidate that claim. And so QE heard me describing this in a hangout, and then he took that my description of the problem as being that, but I was only characterising it I was putting their argument by saying if their claim about way we describe horizons is true with geometric horizon, then they could make that argument, and they would only need to find one exception to disprove us. But because we don't make the claim that the geometric horizon is the horizon, you see, the whole premise of quantum erasers argument is invalidated. So,
and just to be clear, the logic of the argument. So I don't think these guys know the difference between valid logic and sound logic.
No.
So the argument itself is valid in that it follows the logical rules correctly, but it is not sound because the first premise is false. So you've got to make that clear as well.
Absolutely right, Roohif, Glenn. Absolutely correct. This is in a sound argument, as Roohif just explained, all the premises have to be true, and then there's the logic inside the argument, which is also true, and that just makes it a valid argument. But you can still shove in invalid premises into a valid argument, and then but you end up with what's not a sound argument. You have to have a sound argument to be completely a useful argument. So your premises have to be true, and the argument you use based on those premises have to be true. And unfortunately, with QE, his premise, which is globers believe that the geometric horizon is what you see, where it visually is not true. No sensible glober has ever made that argument. So the whole premise of this argument is invalid. Well, I suppose I could quickly move on. Is it worth me, before I describe the observation? I've got this in terms of the observation, and then we'll perhaps go back to how horizons work and how refraction goes. So this is the image that QE created, and Blue Marble knows all about this as being rather. Blue Marble has done a very good video just recently about this issue and goes into the premise, the incorrect premise that we've just described. I was just talking with Roohif there about the geometric horizon. No one claims that geometric horizon is what you see. No glober does that because they know that light bends. So here's the situation. Here is Miramar Beach in Santa Barbara in California. Here is up here is Miramar Beach where the blob is, the pin, and there are two oil platforms, Hill House and Habitat. One at 10,031 meters, Hill House, and the further one, Habitat, at 15 kilometers and 80 meters, with the miles equivalent there. So that's what they're nice, and it is a very good actual thing to pick on because they're in a line, which means you can see things one behind the other, and the relative positions of each one to the other, which is useful, and you can spot any sort of refraction behavior. So, but here is the actual original image that was from a video by BMLSB69. This is taken about 3 years ago, and this is the original image. And you may have spotted. So this is the one that QE has just manipulated in some way. It's just a version of what I'm just showing you here. And you may have noticed that there's some rather telltale signs of something rather odd going on here with these cranes. That is not normal at all. You will be very, and what's more, this is not just some temporary thing. It's not like this was captured as a fleeting glimpse of some warm air going by or some fleeting atmospheric condition. If you watch the video, it's very stable. It's just sitting there doing this. And this is the Habitat, in the distance here, and this is Hill House, the nearer platform, which is at the so this is at 6.2, and this one is at 9.37. And there's some key points immediately to take on board from this image is that you can see the shadows here underneath the platform, which means it's not being cut off. We are actually seeing the water underneath the platform legs, so there's no possibility of that being cut off by some horizon. And later on I go into the positions of the horizons here, and there is the apparent horizon. That's the thing that we see, and you can whoops a daisy. Oh, what have I just done? What did I just do there? It's because I did it inside that, right? Yes, okay, I see. Yes, so there is the apparent horizon there. That is the horizon what globers call the apparent horizon. It's the horizon where the sky meets, sort of, it's a bit blurry, sky meets the water, and you can see that is above and behind these platforms, which are... but the geometric horizon, this was taken from about 1.5 feet. The idiot who took this video can't even determine, and it's very clear from his video, he's at about 1.5 meters and not 1 foot, as he may have claimed. And that would put the geometric horizon somewhere where my pointer is there, something like that. But it doesn't really matter. The point is, when I'll be describing it later, that there's nothing about a geometric horizon that you can see visually when you've got refraction and you've got bendy light. The geometric horizon is just a function of light moving in straight lines. So key points of this thing is the horizon's there. We are seeing where the legs meet the water. There's nothing being obscured. There's only one horizon. That's the apparent horizon, and I'll be describing what's going on there later. And this little boat here, and you can see all the refraction effects. So so that is right. So that's the image breakdown, and this is what the platform looks closer to. And this is another flat Earth idiot who tried to do some image analysis, and he tried this. Sorry, some of this is the stuff with on red and white is mine. He's put in the yellow lines and walkway pipes and 198.9 inches. He managed to acquire this image close to of the platform, but he didn't realise that he thinks the vanishing line, in other words, of this image, he thinks. Sorry, I'm describing something else actually here. That's because. The other thing the guy did, besides this image, he also did a video in which he did this image as well, and he's actually hidden this version of it. In another video which Big Blue spotted, he took some images on another day, and someone's bashing something.
Sorry.
And on another day, so this is, and in the video we can see that he's in the same position. And he gets this image, and this you can see now that habitat is cut off, and this hill house habitat, and this chappie did this analysis from this, and he presumed that this line here, this vanishing line as he called it, is this line here, but he's mistaken. He's mistaken this level to be that, and in fact it's this one up here. Is the line because that's got the crane coming out of it, and you can see here that
that's the other platform too. That's not that platform.
You don't think that's habitat?
No, I know it's not.
Right, he claimed
that's
it was.
not habitat. That's
right, okay, excellent. Okay, so it's even more work. Oh, that's okay. That's even more impressive, right? Right, so. Big Blue has just recently done atmosphere, which is worth investigating, and so we then have the thing. We've now got two images. One with the image the same guy took here, and he's now hidden this video. Actually, Big Blue, how did you find this video of his? Because you found it, didn't you? This was a video you were referencing in one of your videos.
Yeah, it was actually on another channel, referenced on another channel.
Ah, that's right. So you found the one with all the blue image, and then it linked to the original. Right. Yep. I thought that's what you must have done. Right. Okay.
That's what happened, and this is now
unlisted.
Unlisted. Yeah.
Yeah. Great. So the guy obviously sort of realised that by showing this image here, that he was giving evidence of the fact that this is being obscured by the curvature of the Earth, and he removed that, and then he just put in the obscured one. The one where you can see much further. And
he does have another video where he does a similar thing, and he's up at about 75 feet or so.
That's right.
And he does show the normal situation where it's obscured at the bottom, as opposed to the one day that he went there and there was extreme looming. And that's still public.
Is that for habitat?
Oh, I don't know. I think it's Grace.
He did do some other ones, and so you've got to be careful you're not getting confused between the habitat one and the other ones.
Yeah, it's not these ones you're looking at now, no.
Right, okay, yeah, Right, that's what I thought. So, but he does move up to 35 meters, and this is some video that Plain Truth has just done recently. He's been down on there for some time, and he's also found, guess what, that these platforms are hidden. He's in the very similar place to the chap who did and he's
in exactly the same place.
Yeah, indeed. I think he's trying to get a little bit lower, and he's finding exactly the same situation. So this is from his recent video, and you can see he's getting some inferior miraging here, and so these are all three. This is on another day, I think, where it's slightly different. Yes, these ones are the inferior mirages, and the other ones he had up here. Oh, he did some other ones that were very blurry that didn't have an inferior mirage. But okay, I think all these three might be on the same day. So he's also finding this. These all platforms are obscured, and if you then overlay, I think Blue's also done this. If you work out where the platform would be, the legs of the platform, you would find they would be there. And if you then overlay the image that I didn't show here, the images here I've acquired of the platform from other angles of habitat. Can you confirm these are habitats in case I've made a mistake, Blue? This is from the other side. This is from the other side. This is looking towards shore. The guy claimed it was habitat.
I think that maybe. I think that's habitat. Yeah.
Right.
Yeah. That's habitat. Yeah.
Yes, it's from the other side.
Yeah. Yeah, that's the flare pipe on the right-hand side, which appears on the left side in the images we've been looking at. But see where the helipad's on the left here. It's on the right.
That's right. Exactly. It's swapped round. So what I did is I swapped it round that particular image and then overlaid it. And I did the calculation using the thing I was showing you earlier, and I think Blue has done this also. Yes, in fact, I definitely know you have. And if you do this and you come here, and I just change the transparency on here, you can see that in fact it matches very closely. And for instance, this crane over here matches, and the positionless platform. It's it's not quite the opposite side, but. And from my calculation as well, it agrees with this thing. So that's where the legs. Oh, and the point is, in these images, I'll go back to the other image earlier. It's compressed. When you have these, it's when I go back to when we were looking at this, when we were looking at the original image, and as Blue spotted as well, this image is heavily compressed, and you'll notice here these features here are all filled in. And if you actually overlay, I haven't had time to do it, unfortunately. Just one of the things I was trying to do today was to overlay the original on here. You can see that this has undergone all sorts of strange effects. In fact, I think wouldn't surprise me if there's some sort of layering just to match this as some sort of inferior sort of miraging going on between here and here. There's a duplication, and this is certainly stretched up. And so, it's considerably stretched up on that thing. Exactly. And that what happens when you get this situation? I'll describe in a minute what this actually is happening in terms of the refraction. What happens is that you tend to get compression the nearer you get to the ground, and then you also have these obviously having some other stretching of this thing. So this is undergoing all sorts of wacky refraction effects to account for that, and the same is happening to the horizon. We can see to the horizon, and it's because there's what I'll just describe in a minute as there are the refraction is. And I've been speaking to Andrew Young, and I'm going to change. I used to use super looming, but now he said I should really call it extreme looming. He doesn't like the word super. And in that case, you have rays that will actually almost follow the curvature of the Earth, as well as having these unstable conditions as well. Stop me if you ever want to stop me, Blue. Is there anything you want? Yeah, do you want to? I mean, feel free to chip in any way you like on any of the issues. No, keep going. You're doing fine. Right. Okay. So we've established for a start that this image is wacky, the one that we've established that the normal condition. Oh, so what I haven't done is the calculations for. Unfortunately, I haven't had time today to actually work out whether the correct hidden is values there. But I think I've done it on a previous occasion. In fact, I could do it semi-live while perhaps someone else does some presentation. But I did actually do on some of it, and I actually established that the normal version of events, this one. That it's very close to being the standard refraction conditions we're missing from this. Now, someone called Ranty Flat Earth has claimed that this is due to a swell, but it doesn't work. He's claiming this is, if you have this at a 1.5 foot swell, it can account for what we're missing here and here, but it doesn't work. Right, but I want to just talk about horizons and how they work. And I've got some little diagrams here somewhere to describe them and how. Yeah, so here we go. So first of all, yes, I'm going to very quickly describe refraction. I mean, people have heard this before, but I think to fill in people, there's a laser tank image. Here we go. This right. Here we have a laser tank, and this demonstrates the principle, and then we're going to move it into the atmosphere. But first of all, we're just going to demonstrate the principle of curving light in a medium which is changing its density and refractive index. Here we have a tank full of dissolved sugar. Greater density of the sugar at the bottom than the top, and that means, and the refractive index of things is very closely related to its density, and so that means that you have a greater refractive index of stuff near the bottom of the tank than the top, and light following Snell's law, which I've got up here. Sorry, it's down here. Apologies. Where have I got the damn thing? Here we go. Snell's law, which is this rule here that when light, so we've got light starting off in some water, and when it hits a through a medium boundary and into a lower refractive index, it bends away from the normal. The normal is a line that's perpendicular to the medium boundary. The light bends away, so you get this sort of situation. Here, I'm describing here, so if you've got lights coming in horizontally, it will bend down following Snell's law, and it do the other things as well I described here. So it bend away from the normal going, and what's more, light is reversible, so when light going in the opposite direction will bend towards the normal. So it bends towards the normal when it's going into areas of higher refractive index, and it goes away from the normal when it's going to areas of low refractive index, and that means that light will therefore bend down. If it's got a boundary here, it will bend down towards the refractive the medium with higher refractive index. So it always bends towards the areas with higher refractive index. So that means in our tank situation, the light will bend towards the area with so it starts off going upwards. And so it's going to gradually, always changing its direction towards the area of greater density. And actually, at the end there, it is actually starting to curve down. And if it was left, if the tank was long enough, and there are other examples on the YouTube where this light will actually will carry on bending down and form an arc. So basically, every light likes to bend. If there is a variation in refractive index, it will always bend towards the area with higher refractive index. And so I'll just do an examination here with the Snell's law we showed you earlier. It bends away from the normal when it's going, because the high density here, lower density there means it bends away from normal. In other words, it becomes more horizontal. And when it becomes horizontal, in other words, it's bending towards the denser medium, and it does the same when it gets over here. It bends down towards the denser medium, and so it forms an arc. So we can see that's what happens inside, reality. This is a real picture. This is what happens in reality. So, and that means that if you imagined you were an observer here, sitting on this point where the light is horizontal, and the light was coming up from a little object here, which is the little top of a lighthouse, you would perceive that the light is coming into, and let's imagine it meets you as horizontally coming in here. The way your mind works, you presume that the light's coming in straight lines, and so you would actually perceive the object here, even though it started off light down here. And we're going to develop that a little bit further. So what does that mean in the atmosphere? Well, the atmosphere, this is a structure of the atmosphere. This is meters, the height of the atmosphere here, vertically, and this is the ratio of whatever property it is we're describing here, pressure, density, or temperature, as along here. So 1 is the highest, and 0.2 here is the other is the least we've got. So something like temperature will decrease as you go up in temperature. It's warmest at the 0, And the density, which is the thing that determines refractive index, also decreases as you go up. So basically, the atmosphere becomes thinner as you go up. Mount Everest up here is 0.3 in terms of pressure. It's not nearly 0.4's worth of density. So in other words, it's pardon me. Therefore, the refractive index will be 40% of what it is down at the ground, relative to 1. So it's actually, I won't talk about that. It's refractivity. But anyway, so this is what happens. So following on from that laser tank thing, what happens in the atmosphere? If you imagine the atmosphere is just a solid, uniform, homogeneous, anisotropic substance, then light still travels in straight lines. This is glass. So imagine we had a layer of glass on top of the Earth. Light would come out horizontally, and then when it hit the boundary of the glass, it would then bend away from the normal, because this is how density, it always likes to bend towards the high density thing. And if you imagine there were more layers in here, then you would get those refractive events happening at every boundary. And then, of course, if you had a sort of many layers, it would then form a curve. And this is like our atmospheres. In other words, it's less dense up here, more dense towards the surface, and therefore you're going to get bending of light like this. So what does that mean for an observer? Well, that means that this is what happens to light rays. So here we've got our little lighthouse here, and light rays will bend following the curve, in effect. Now, this is as a result of the structure of the atmosphere. And there's a standard, for a standard atmosphere, there's a standard bend here. And this is slightly exaggerated here, but it basically follows the Earth because there's a gradient, if you can think of it as radial lines coming out of the Earth. And so it's going to always be bending towards, so even though it's, whatever it's doing, it's always going to bend towards the Earth. Now, the way you can work out, now you can see I've written in here the geometric horizon, which is what an observer would see as the thing where a line that's being emitted from some point on the Earth leaves at a tangent and arrives at the observer. If you were to go any further over here, a line of the tangent would not make it to the observer. So this is the first tangent, a line that will make it to the eye. But when light's bending, then you can see further. So in other words, so if I can show you how this works, if I click on this, I change the angle, whoops, of this curve. Come on, where's the thingy? Where's the thingy? Please tell me where you've gone. Oh, there he is. Right, so, because the horizon is defined as where a line that hits the Earth at a tangent meets your eye, and that's the position there for the thing, you can do the same for these curved lines. So, for instance, I can say, oh God, I've got the wrong. It'll still work, but it's just slightly more fiddly. Hold on, I'm going to have to fiddle with this. Apologies. No, I don't think I'm going to do that. I want to delete this one. Right. So, yeah, sorry, I haven't been able to prepare this as well as I might have done. So, if I rotate this, you can see, so this curve here of this light is how light will bend in the atmosphere. No matter where it's going, approximately this is, because obviously when this lighthouse won't be as high as this in actual reality, it will be much closer to the ground, but this is obviously demonstrating it. So this is what how light will bend in the atmosphere. So the question is, for light, what point does light that's bending like this from the observer touch the surface of the Earth? And you can see it's like there, and you can see that I've actually positioned the lighthouse here at the apparent horizon. That is the horizon that you will see because light is bending. And of course the geometric horizon has no interest. It doesn't do anything useful. There's nothing special you would see visually about what the geometric horizon, and that's why the argument that is offered by QE with the Black Swan thing is completely irrelevant. All globers know that light is bent, and we all know that the geometric horizon, which is there in this particular case, is irrelevant, and the actual horizon you do see is the apparent horizon, which is where the light that's bending forms a tangent with the Earth. And so this is the situation I've got here with the actually I positioned this lighthouse on the apparent horizon. So what does that mean for how you see things? Well, this is what happens. This is the situation here with light with no refraction. And as you saw, I put the boat there on the geometric horizon, so it sits on the geometric horizon. And you should also see that this area in yellow is obscured by the horizon, so that you will not see this part of the lighthouse. In the first bit of the lighthouse, you'll see this second window here, and that's what you're seeing here. This just underneath there is the first part of the lighthouse you'll see. But when you have curved light, using these curves to transmit it, you will find that everything is... Now, I used to use the phrase loomed up, but I've been speaking to Andrew Young, and he says that loomed up has very special historical meanings, and you shouldn't really use it for standard refraction. So I'm going to say raised up rather than loomed up. But everything is raised up. Everything you see, whether it's next to the geometric horizon or anywhere in between, even if it's a tree just outside your front door, it's actually raised up due to standard refraction. And so here, when you kick in the standard refraction, as I've done here now, so this is without standard refraction, this is no refraction at all, and this line, this purple line here, is the horizontal eye level for the observer. So that's this purple line here. I'll have the observer here, oops, on this one here. The purple line here was the horizontal for the observer at this point. So I've maintained this in this view in the same place here. And so this, you can think of this like as what you would see through a theodolite, which had not moved between the two positions. And then I switched on refraction, switched on the atmosphere between these two, and you'll see that the boat is raised up, and actually, I think when it's this extreme, I think Andrew Young said you could use looming, and the lighthouse behind it is also loomed up, and that's what refraction does for you. And so hopefully I've now explained what horizons are, what looming is, what raising up the standard refraction, and where and why it's absolutely ridiculous for any flatty to go on about the geometric horizon when we are saying the geometric horizon. So here you can see here the geometric horizon has no special visual properties at all anymore. There's nothing special about it whatsoever. There's nothing it does of interest to you. And you can see here the horizon has jumped up, raised up, or loomed up in this case because you've got extreme refraction to this position. So this is what you would actually see. And indeed, there are videos from flat earthers who out of Sydney are looking outside their window and seeing the horizon move up on different days by different amounts caused by refraction. Flatties claim that the horizon has never moved up as a result of refraction or looming. They say that just doesn't happen. Well, we've actually got a flatty taking videos out there. In fact, Roohif put me onto this actually, of this Australian in Sydney who's taking videos seeing the horizon go up and down. And he's got a cliff face that he can match the horizon against, so he can know in absolute terms that the horizon is moving up and down. So hopefully I've explained geometric horizons, the apparent horizons, how you work out where the apparent horizon is, the fact that geometric horizon has no relevance to us, and I've probably said I did want to go into debunking in more detail the claim that the swell is responsible for obscuring these platforms, but I just haven't had time today. So I don't know if there are some other issues I want to discuss, but I don't know whether other people want to chime in at this point and say anything I've missed or any extra bits.
I'd like George to speak about the pressure gradient. Ranty made a claim the other night. Ranty claimed that George said the pressure gradient was negligible or less important than the temperature gradient. So if George can clear that up, that'd be good.
Well, the formula... Sorry, I just, for fear of butting in on George's thing, the formula for the curvature of that ray that I was just showing you is given by this formula here. Butt in, George, if you want me to stop. There's a formula that describes what curvature happens in the atmosphere. And, sorry, it's taking me a bit long to get there. I've had a bit of a harrowing time. come on. Here we go. There's a formula. Just up here. Oh, right. Sorry. One thing I should have mentioned. The rays that I was talking about there, the curving of the rays, they are actually described by something called a K value, how close they are to the curvature of the Earth. A K value of 1 gives you a curvature the same as the Earth. A K value of 0 is a straight line. And a negative K value of 1 would give you the reverse direction. These rays here are responsible for inferior mirages. And how much the rays curve is given by this formula here, which tells you what the curvature K value is for a particular pressure, temperature, and temperature gradient. And
is that for visible light or radios?
Yes, visible light.
Visible. Okay.
Yeah. And so actually the dominant thing that causes it is actually the temperature gradient. These because the temperature gradient, from the temperature gradient you get a change in the pressure gradient. If you do the calculations, as we've done, Philip and I did with the ray tracing things, which won't necessarily go into here. You can. It is the temperature. If you have the temperature at any point from the temperature gradient, then you can work out that determines what the pressure is going to be, and thereby the density. So from the temperature, almost, although that from the temperature gradient, you actually determines most about the refractive properties. So, for instance, if in the when we were modelling in this ray tracer, the behaviour of the K value here, this is what the temperature is doing at a particular height, where this is very close to the ground, is where almost all the action occurs, and you get a change here of just half a degree across 20 meters, but that's enough to cause inferior miraging. So this is the temperature gradient, and this is what the index of refraction does, and you can see that it is constant from 30 meters all the way down to about 5. Then it sort of does this flip caused by this change in the gradient of the temperature here, and then this becomes more extreme here. So this is what the index of refraction does, and this is what it does to the K value of the curvature. And you can see it goes wildly from, this is the 0.14, so I didn't mention that, did I? Then the K value of the curvature of the ray up here. Oh, Jesus. This is the normal standard refraction. This red line, near 0.14, or 0.14 actually, is regarded as the standard refraction line. That is what standard atmosphere gives you, that 0.14 curvature. And obviously something going to 1 is quite a lot more substantial. So that the 0.14 that you saw that graph go up here, this is 0.14 here, that's standard refraction. And so, in other words, all the way up here from this point onwards, it's standard, even though the pressure and pressure is changing and the density is changing. It's doing it at this rate, which means actually the K value remains not quite constant, but it remains moderately the same for going up as you go up. But when you get down, this bend in the index of refraction, the change in temperature. Sorry, this index of refraction there, that's the temperature. This is the index of refraction, and this is what happens to the K value as a result of this change. And you can see it, then you get these -5 value here, which means and this is what causes an inferior mirage. The fact that you're getting negative curvature near the ground, very near the ground, and that means these yellow things here, which I'm showing you, these things. So -5, you see, these are -4. That's what the light would do over this distance. Obviously, this is on a huge scale, and if I were to show you this to scale, it would only be a very slight increase. Anyway, sorry, George, if I've interfered with what you were trying to say or something, or your answer. Do you want me to stop sharing or something, Karen?
George is muted.
Oh God, George. Fine. Did you want to? Shall I stop? I'll stop sharing now, so George can. Did you want to share anything, George, or anything?
Do you want me to address that now? I
can address it later. I rudely interrupted you.
No, you didn't interrupt me. I didn't start.
Okay. I rudely interjected then.
I mean, I can address it a little later if you want to continue on.
No, I'd be more than happy for other people to chip in here. I think I've said more than enough.
Well, I'll tell you what. Give me about 5 minutes. I need to deal with something with Con here.
Okay, all right. So, okay, perhaps I'll. Okay. So there are other issues I was thinking we would cover in this. Blue. I don't know if Blue. If there was Blue. Were you happy with my comments about your video? Is there anything you want to say about that, or?
Well, no, all I'll say is you've got a lot more experience with these sorts of observations and analyzing them than I do, and I don't make any pretense about that. I've told people, and I've said it many times in Hangouts and on my channel too, that I generally try to stay away from these damn things.
Indeed, you do. You hate these watery things, don't you?
yeah. As far as I'm concerned, the Black Swan or Black Turkey or whatever you want to call that damn thing, to me, it's a very useful video, in that it serves as a perfect example of something that when you see that, you should know immediately it goes directly to the trash bin. That's all it's worth. In my mind, you're just looking for arguments at this point.
Yeah, I mean, as you pointed out in your video, that this wiggly stuff here should warn you off trying to draw any conclusions about this. What the hell is going on? It's very dangerous. And also, I said, Blue also spotted the compression in these images and the fact that it did all this wacky stuff. But, there is this sort of horizon line thingy here, and that's because I believe that the refraction in this picture is very close to k is equal to 1.
I think it's over. I think it's above.
You think it's above 1?
If this was taken at if this was taken at 1 meter or something, you've got to look at where that horizon line intersects the structure of the platform, and it clearly intersects higher than 1.5 meters or 1 foot or whatever it is. Therefore, you're looking up, like optically, you're looking up to it. So it's almost a concave Earth.
Rumpus, I can show this if you want.
Okay, let me just show you what this. So I believe, looking at that thing, that in fact you've got a k value for the curvature of the rays of about 1, which means in effect you would never have any obstruction. The horizon would never obstruct. Obviously, you get attenuation and Rayleigh scattering, which would mean the light just gradually fades into nothing and disappears. But it means you don't have a horizon, because the light ray curves all the way along here, so the Earth's geometry doesn't.
It appears flat. Yeah.
Exactly, it appears perfectly flat. Exactly. And that's one thing I didn't mention in this lighthouse thing. Was that so of course this appears much flatter as a result here. Even of these curves here, you've actually flattened out. You can see further than geometric horizon. So just simply by these rays curving around the Earth appears flatter. Though in this particular case, the rays weren't curved enough. But imagine if these rays that I've got here were more curvy, then in fact this eye would be able to see all the way around along here. There would be nothing. There would be no point at which it touches as a tangent, or it's following as a tangent all the time. Sorry. So do you want to go ahead, Dean?
So just to demonstrate something what Glenn just pointed out, because I did take the survey data for the things. I'll share my screen. So I took the survey data for the platforms, and I put them into a 69 mile 1 degree of the Earth, which I'm hoping we can all see, which is this huge strip here. And that, just for any flat earthers looking, is 1 degree of curvature. That's 69 miles. And then I've got a few cameras, but my cameras sit I've got one at 30 foot, one at 1.5 foot. And what we're doing is we're looking through the 1.5 foot at the moment on the left. Now, with 1 degree of curvature, and obviously 0 refraction, this is what we would expect to see. But a very interesting thing happens is in perspective on a flat plane with an elevation of 1 foot, the image that we are looking at, that is this Black Swan image, is impossible on a flat plane. Because if I change the curvature on this planet little thing to 0, this is what we would expect to see. Now, the important thing here is because we are at 1 foot, or even if it's 1.5 foot elevation, because of the distance and the acuteness of angles, the difference in our vertical between the bases of these towers is insignificant, yet we see quite a significance. Now, we know we're not looking down. We know it's a very low acute angle. So the only thing that I can do now is say we'll have a negative effect, and this is what I've had to do, which is a negative 0.0 concave Earth to actually produce that image, which is why I support what Glenn just said, Roohif, when he said it's over a K value of 1. It absolutely is, because the estimated vertical difference between the bases of those two, we just have to assume the following. Those bases intersect the same water, and that water is level, and that's it. That's all we have to assume on that side, and then we say, well, we are above the water. Now,
yes, because effectively, sorry to interrupt, but what you're effectively saying is that these are at the camera's level, the base here and the base here at camera's level, and we talk about the perspective causing things to get smaller around your center of vision, but our center of vision, our eye line, is actually at next to nothing, almost at water level. So in other words, these two things should line up at their bases, and because we can see the bases and they're not lined up, therefore we cannot be on.
However, the one caveat here is to produce this image on a flat Earth, we could do it, but the camera elevation would have to be probably about 60 foot.
Right. But we know it's not, yeah. And also, actually, what you were talking about, convex rays, yes, Philip and I actually modelled how you would get the impression of being on a flat Earth. What you'd have to do on a flat Earth to give you the results that we see for a spherical Earth. And it turns out, as you correctly pointed out about the convex rays, you'd have to have convex rays, and what's more, that to maintain that temperature gradient, you would actually have to get less than absolute zero, just a few kilometers up in the sky. So it doesn't work. But I just want to re-emphasize what you were saying here, Dean, about the base of these things. So even the flatties, I think, agree that we can see the base of these objects because of the shadows on both of them and where the water is, and because we're even when you allow for compression, we can. I haven't done this, unfortunately. I should have done it. I think Blue had a bit of a go at this, putting over this to find out to compare where the base is here, and we're happy that we are looking at the bases. Blue, are you happy that we're looking at the base of these things? I can't quite remember if you're.
No, I'll tell you if you had the observation from 35 feet that he made, it doesn't. I'm not totally convinced.
Okay, no. All right.
But,
okay,
but
cool.
it's so screwed up. I don't
You're
know.
Just saying it's not okay. Well, perhaps Blue and I will resolve this between ourselves one day. We'll have another hangout on it about it, perhaps go into the detail of this particular aspect of it. But I personally believe that because of the shadows and because of the compression, that you can say that you are seeing the bottom of the legs on the water, both here and here. And therefore, the argument that Dean is making, which is an excellent argument, that if we are the same level, supposedly this camera is only about, it's about 2 feet, 1.5 meters above, which effectively, as far as this thing's quite large. And there's this thing here is 9 meters tall between there and there. So we're effectively right down here, which means, as I say, everybody knows that things reduce around your eye line. And that means that as our eye line matches the base of both of these platforms should have the same vertical position in our field of view, and they don't. So they cannot be flat from just that basic thing. And then we were talking about the horizon. So there's the horizon. That's I believe because the K value. I believe the K value is 1, but I'm not quite sure why. I think Dean and Roohif are saying they think it's more than 1, but I believe it to be about 1.
Well, put it this way, Rumpus. I can invalidate what you said with one simple comment, and you can do the math. If this camera is 1 or 1.5 feet high, and the base of those,
I think it's sorry to interrupt you, but I think it's 1.5 meters high. The guy in the guy took the video is an absolute idiot.
Oh, is it?
It's about 1.5 meters.
But even then, contemplate this. Even at 1.5 meters, if you've got an object at 9 miles away, you can work out the angle of that, and you can work out a perceptual horizon that would be infinity, and it still wouldn't be as high as that point, the horizon that you've got there.
Right, but you don't know
if your line of sight from 1.5 meters.
But hold on, Dean. Sorry, Dean, you don't know what angle he's got the camera at.
No, it doesn't matter what angle.
Yeah, it's irrelevant, the angle.
Well, hold on, sorry. But when you say that it's as high as this, I mean, you're saying, do you mean the angle?
What I'm saying is, if you've got the survey data, which is A, the elevation above a flat plane, and B, you know the distance to an object and you can see its base, you can work out where an infinity line would be, and it is less than the height of that horizon.
Yes. If the camera is at 1.5 meters and you draw a straight line, like a straight line of light, between your camera at 1.5 meters to 1.5 meters on that oil platform off the water, the horizon is above that. Which is why we think the K is greater than 1.
Laws of parallel lines, Rumpus. Think.
Yep.
Think.
Parallel lines on a flat plane.
Right, but because
Rumpus, look at this.
Actually, right. Sorry. Sorry. One point. It's actually. You can reuse the argument again because these two things. If it was flat, if you did have, you actually. I think I have to agree with you. Actually, if K was equal to 1, this would be perceived as flat, and these two bases would be aligned. So in fact, K can't be 1. I don't know if that's the point you were trying.
The bases, if you're any distance above the surface, then there will be some separation between the bases. But not this big.
I mean,
not this big. Correct.
You're so close. I mean, 1.5 meters. I say this thing's 9 meters high. You're so close to the base of these things that if you did have K is equal to 1, then just like the flat Earth case, which makes the world look flat, then these bases would be aligned. And so, in fact, I'm agreeing with you now. Because these are not aligned with one another, you cannot have K is equal to 1.
Yeah, I agree. But there would be a minuscule difference in the bases because you're above the water. Minuscule difference.
Right. Sorry, I just got interrupted there. So Dean, could you make your? I'm a bit groggy from my earlier experience. Could you just repeat your argument again? I'm just feeling a bit. I've had a hard time.
So the laws, like Glenn was saying, the laws of parallel lines dictate that whatever elevation we are, let's say we're 1.5 meters, that 1.5 meters will stretch along to 1.5 meters up from the ocean, up the bases of both of those.
Yeah,
if you take the furthest one and go 1.5 meters up, and then we draw a vector, a straight line, it hits the water. It doesn't hit the horizon. It should intersect with the horizon, an infinite horizon.
Yeah, the horizon is above eye level in this photo. Therefore, concave Earth.
Yeah.
And how are you? Because you're saying that the eye level is at the base of the leg.
If the Earth is flat, it would have to be very close to it.
Exactly. If the Earth was and if K was equal to 1, then the bases of these things would have to line up, and the horizon would also. Yes, in fact, so all three. Yes. So in other words, if K was equal to 1, the horizon and the base of the legs would all be on the same level. If K was equal to 1, so that disproves indeed makes incorrect in saying that K. I haven't had a chance really to think about this. I haven't really been working on it all day, but yeah. So you're disproving the case of 1. I'm now agreeing with you. It can't possibly be. But I still don't quite understand your argument because the eye level here is is effectively at the legs of the bait where the legs meet the water. Effectively, your eye
I'm
level.
not even looking at the one on the right. I'm ignoring the one on the right because the elevation. Once you gain elevation, there will be a difference in the bases of them, right?
But it's so tiny. We're only at 1.5. You wouldn't be able to tell it at 1.5 meters. I don't think you'd be able to tell that.
No, I agree, but there'll be some.
So your argument is if the horizon caves are one, you're saying the horizon should be there. Is that what you're trying to say?
The horizon should be 1.5 meters from the base of the.
Yeah, but 1.5 meters is,
right.
1.5 meters is just a pixel or two.
Yes, there you go. Well done, Rumpus. Yep. Now let me share my screen. I'll show you what it should look like. So I'm going to share this now. Right. So what we've got here is those platforms on a flat Earth with a 69-mile ocean. Now I could increase this to 20,000 miles. The horizon will not raise more than a pixel. And the point here is we do see the horizon higher than it should be, therefore not flat. Concave.
Or flat earthers can actually accept that light bends.
Yeah.
That's the other alternative.
Yeah, that's it. So you get that, Rumpus?
Sorry, someone's trying to get in on this chat. Someone called Jonathan M. Watson. Is that the idiot flat earther?
No, that's okay.
No. He's Glober.
You can let him in. So it's fine.
He wants to come in on the call. Who is Jonathan M. Watson?
Right, so
who is he? Sorry, could tell me who Jonathan M. Watson is? I didn't realise I had him on Skype.
I was just a guy. Let him in.
He's good.
Is he? Okay, all right. Okay, I'll let him in then. Okay, right.
And then just something to hit the point home as well. And I just want to show this because then I'll have to bugger off. But on a flat plane, if we've got two objects where the base sits on that flat plane, we can see what happens here is when I'm looking down, the object in the distance, the base of it is higher in our vertical vision. Now, the only way for me to get that lower is to be below this flat plane. That is the only way in perspective. If I'm above, it will never. But if I'm below this flat plane, now we're looking from the underside of it, I can. So, I draw your attention. Can you see the image that I've got on screen at the moment?
Mm-hmm.
I draw your attention to this. So it doesn't matter whether this is a tidal wave. It doesn't matter whether a fucking sea creature is under here causing this to happen. It's irrelevant. When we show that the bases of these platforms do not sit at the same level and the one in the background is lower, there is only one simple way for that to happen. It's not fucking flat.
Correct. Did you hear Brian the other night wanting to check the tides for the platform?
Well, it's irrelevant. It's irrelevant. The argument is irrelevant. It doesn't matter whether there's tides, sea creatures, or anything. This is simple.
They're not fucking floating. They're not floating in the ocean. It's hilarious.
You're telling me that the horizon can never be in front of an object on a flat Earth, right?
Yeah.
The bases of the object, an object further away on a flat Earth, the base of it will always be visually above the closer object.
Yeah.
And if it's below, it's not flat.
On a flat Earth, you can never have a horizon between you and the object.
Oh, correct. Yeah. There can't be any obstruction on a flat Earth.
It always has to be behind the object.
Yep.
And I'll just conclude with this because I might have to get off in a second. But on this, when we do, I did match this up to 1 degree of curvature over 69 miles, which is what we're looking at right now. So this is the geometry. And obviously, if light bends, this starts to be pulled up a lot more. Now, on a lot of the images, we see less distortion of the image, as in these cranes are all straight and lovely, and we see more of this effect. The only time when we don't see this is when these cranes are wavy and bendy. And this just comes down to pure logic. Which do you think represents reality more? The oil rigs made out of jelly, or the ones made out of iron and steel and straight girders? And that's just common sense.
Does someone else know this Jonathan M. Watson? I see it doesn't seem to want to let me add him to the call. It's driving me nuts.
No, he's actually just said in chat that he tried and couldn't get an answer. So
yeah, well, he tried to call me, and that would have meant I would have come out of this call. But I'm trying to add him to this call, and I've added him as a contact, and I can't get him.
I'm adding him. Jesus Christ, computers, Rumpus, technology.
Well, it's not coming up on my list. The list of people I can add is not coming up, even though I was made him a contact.
Whatever.
Okay. I'm having a bad time, obviously.
Get a Mac. Get a Mac.
It just would not show him up as a bloody person I could add.
Does it make a difference if you're the person that initiated the call?
No.
All right,
Anyway, he's in anyway. Thank God for that. So I missed your point, Dean. But anyway, if everyone else heard it, and sorry, could you just quickly summarise your point again for me, Dean? I guess I missed it.
Yeah, you need to get a Mac. End of story.
No, not that point.
Oh, okay.
The previous point you made while I was being hassled. Oh, never mind.
I've totally forgot now.
No, okay, forget it then. Just carry on. If Jonathan then Watson's got a major point he's very, very keen to make, I mean, you can speak up now and we'll listen to you.
Can you hear me?
Jesus.
Yes, we can hear.
Yeah, you're very loud.
Very loud.
Turn the volume down, please. You'll speak
Oh,
up.
Yeah.
sorry.
Volume.
I don't have a volume control.
Oh, it's John Watson. Oh, that John Watson. Oh
God.
Jesus Christ.
Was it the M that was throwing you off?
I thought I had him as a contact anyway. So sorry, John. Oh, right, yeah.
Well, you fucking should be.
Thanks, John. I'm having a rough day at the moment. You're adding to it.
Well, you can say sorry later. Sorry.
Right, thanks.
I just what I kind of want to say is when all this talk about exactly what's going on when you're making these low level observations, it is quite interesting. I find it really interesting. I do, and I think it is worthwhile looking into it. But the fact remains that if you want to make accurate observations about sort of the nature of the Earth, etc., you've got to avoid these low-level observations.
Absolutely.
And so, I mean, you don't. I mean, no surveyor would attempt to gain accurate observations at this time. And I really don't want to. I really don't want to rain on your parade because I think it is good that you kind of try and kind of decipher exactly what's going on. But I wouldn't say that you never will. But it's not ever going to be cut and dry.
I think there's also the problem that flurfers will never understand what we're talking about anyway. I mean, that's why I prefer going into enemy territory and talking to those guys. I mean, this is interesting for Globers, but flurfers are fucking idiots, so they won't even understand it. So there's that aspect to it as well.
But I think it's not a dead end. It is really worthwhile exploring this stuff. It is really interesting. But what you're swimming in is the grey area that flurfers depend upon to try and make their point.
Yeah, but John, we're invalidating their point. And for instance, hopefully I explained earlier the difference between a geometric and an apparent horizon and how that's calculated, and they don't understand there's a difference. Well, they think that we think that the geometric horizon is what you see as where the sky meets the water, and we don't do that. And I've hopefully explained how you end up, even though we believe in a geometric horizon, that there is a point on the Earth where a flat line, a light ray would hit a tangent on the Earth. We understand how an apparent horizon comes about that's not in the same position. They're confused by thinking that they think that the geometric horizon is where the horizon is, and we're making it very clear in this analysis that that's not where we believe the horizon to be. And also we're saying, yes, you do get these strange effects near the ground. None of us, I don't think, is proposing that going near the ground is a good idea, but we've got this on the table, and I think we've refuted it by also pointing out, obviously, all the wiggly lines in the shape of the habitat oil platform, that this is unusual and extreme refraction conditions, and that's why you can't, once you understand that the horizon is a function of refraction and you've got wacky refraction conditions, then we can say, no, this is not a valid argument that invalidates the global Earth. That's what we're trying to do here. We're trying to refute at the moment a silly argument. So we're not proposing, no one here is proposing this is something that you should do to try and prove the globe Earth. We're saying, no, we're just trying to disprove the challenge from Flatties that this is a valid argument.
Rumpus. Yeah, I realize what you're doing. I really completely do. We would only see the geometric horizon if our atmosphere was in fact a vacuum.
Or K happens to be equal to 0, John, and that can happen.
It's just incredibly unusual.
Not very often, and it would only be a transient, a temporary situation. But truthfully, that's the entire usefulness of talking about this in my mind. The fatal flaw in their modus tollens argument is the fact that they are conflating a geometric horizon with an apparent horizon, and that is not true. It has never been true, and I've never heard anybody say that. Yet Nathan Oakley and Quantum Eraser will continually hammer on that, and Nathan's not going to give that up. He can't afford to. The minute he admits that the apparent horizon and the geometric horizon are most likely not coincident, then he loses this argument right then and there.
As I said on your video the other day, Blue, the whole root of this is bullshit anyway, because in order for them to have a valid argument, it would also have to be the case that everybody would have only ever have had to have said there's a geometric horizon, and only ever a geometric horizon, and never said that there was any such thing as refraction, and that we don't get different conditions, which obviously isn't the case. I mean, we've been arguing about this for years. Rumpus, of all people, obviously knows this directly from interaction with Oakley, going right back to the St. Bees stuff. That's why he's famous for saying things like superlooming and all this kind of thing. It's why Nathan has his stupid superlooming hyena line that he uses, because for over a year and a half they've been arguing about what refraction is, because on our side, people have been saying refraction is a thing. It does all kinds of weird things. It does lift things up from behind their horizon. That's been an argument for a long, long time. So to then propose an argument that says, well, you never say that, and now it's happening, haha, is just completely false.
It's incredible, isn't it, Al? Because we've been going on about the effects of refraction for 3 years or more, and they responded with, oh, what, you're saying everything's loomed up, everything's refracted, everything's a mirage. And now suddenly they're saying, oh, well, you now got to place it in the geometric position, even though for 3 years we've been telling them everything's refracted. Yeah, exactly. So it's weird, it's a wacky turnaround of events. So it's though they've just discovered refraction, and they say, oh, well, therefore, and where we've been saying you can't use the geometry because it's all refracted, now they've suddenly said, oh, no, you've got to use the geometry, and we're going to ignore, accusing us of refraction one day as being a heinous crime, and now saying we're claiming it, and how unfair is this? I mean, it's almost that the 3 years, they've only just understood after 3 years what we've been saying.
Yeah, it's complete nonsense.
It's amazing.
That's what amazes me, is that, as I say, the programming is so strong with the minions that they actually get away with doing that, and all these idiots are just running around now to all the chats going, oh, Black Swan, as if refraction is a new thing for the globe kind of thing.
And the other odd thing about this Black Swan thing, I know I sort of gave QE the ammunition to make it in a sort of sloganized, easily memorable thing. But we've had many occasions where we've had to deal. I mean, the Isle of Man situation, for instance, there were a number of things that you shouldn't be able to see if you just did it geometrically. And we were having huge arguments about why we could see the Moorgold Lighthouse. And there was Nathan Oakley having a go at people like Paul Voigt saying, oh, well, how come we can see this lighthouse then? It's not behind the geometric curve of the Earth. We're busy saying, well, that's because it's loomed up, matey. It's got refraction. And now
exactly. I can remember that. I can remember Paul literally, actually, they went on to I think it started off with Anthony and the standard atmosphere page and stuff like that, and eventually it led to Paul Voigt bringing up the equation on screen and going through it all step by step, explaining how to work out the K value.
Yeah.
You know what I mean? So this is really, really old news. They've been over all this territory before, so they're basically pretending, it's like as if they can just kind of, it's like the Etch-a-Sketch fucking logic.
Well, I think they've only just understood what we were talking about. They've only said we were saying things like looming, refraction, things are lifted up, they're not in the geometric position, and they presumably understood this to mean we believed it to be in the geometric position. So now they're saying, hold on, you used to believe everything was in geometric position, because they just didn't listen to what we were saying, even though they were shouting mirage at us and looming at us. And we were saying, yes, everything's loomed. And they were going, puh, puh, puh. No, it isn't. We were saying, oh, yes, it is. And then, they, as you say, the refracting hyena bollocks was the weapon they used against us, because that was the argument using. And they seem to have forgotten that was the argument we were using. And now suddenly they've ascribed to us that we're using a geometric, pure geometry argument. Hello? No, never did that.
It's like every way you look at it, it's complete bullshit. I think it's listening. I said that I kind of listened to a couple of sections of the Roohif versus Brian thing, and good. I noticed that Brian was basically copying Quantum Eraser word for word on
what they didn't have a brain.
Particularly, quoting the cherry picked quote about what looming is, saying that it lifts things up from behind the horizon, so they assume that means that the horizon stays in one place while stuff behind it gets brought up from behind.
It's magic. God. It knows how to lift shit up. It just can't lift the horizon up. It's just magic. Yeah.
I mean, you try and explain to them something simple like the fact that it's the light from everywhere. Like all the surface of the water is not excluded.
How many times did I say that to him? Like, objects in front of the horizon are loomed up as well. Actually, sorry, Rumpus. What did Andrew Young say about the historical definition of looming?
Yeah, I mean, you were absolutely right. I thought you did really well to keep on board with that and point out, as I've been doing for 3 or 4 years, that everything is raised up. Even the things outside your front door and over the other side of the road are raised up. And you emphasise this again and again. And then they had the cheek. Someone was in the cheek in the chat, or someone was it. Ranty said, "Oh, you're really being owned here, Roohif." And I was thinking, you did a really good job. You kept on hammering home that everything is raised up. Everything is raised up. Doesn't matter where it is. This side of the horizon, that side of the horizon, it's all raised up. Now you called it looming, and indeed that's what I've called it. But I promised Andrew Young not to do that anymore, because there's an old-fashioned specific term. And in fact, he's got actually in raising this, I've pointed out a fallacy in the way he's categorised things, because on his site, I know you've been there, and in fact you analysed, you did a video on the circulating rays thing. He describes the 4 types of refraction. He talks about looming, sinking, towering, and stooping. Now, towering is just a non-linear version of looming, and stooping is just another non-linear version of sinking. So if you say those are the only forms of refraction, we've always then said, well, because we know that everything is raised up, well, we're going to put that in the looming category. But now but he says, no, you really shouldn't do that, because looming means it's a well-established 100-year-old term to describe extreme refraction in effect. And so I said, well, hold on, that means you've got these 4 categories of the looming and sinking and stooping. But so where do you put the standard refraction, the standard raising of things? And he said, oh, you've got a good point, actually. But so he may go back to his site now and add in, perhaps I'm hoping, add in a 5th category for the types of refraction and say standard, or standard
looming,
standard looming, yes. So
what do you then call something that's loomed up, like a K of 0.001 or something? What do you call that? Like it's loomed up, or it's appearing up.
Yeah, well,
but it's not standard.
His argument, yes, exactly. What do you do for stuff that's been raised up less than what qualifies for looming? What do you call that? Yes. So there's a gap in his definitions, but
between 0 and 0.14.
Yeah, exactly, Roohif. But in that area, what are you going to call that? Or even the bits just beyond 0.14, because looming is a sort of extreme. So you and I think, very sensibly said, well, okay, we've got these 4 definitions on his website. We know that looming means it's raised up, so we're going to call everything looming. But because he only had the 4 categories, so we're going to call that looming. So I think we were perfectly reasonable in doing that. And if you carry on doing that, that's fine. I'm not going to criticise it for you. But I did promise him that he says that historically there's looming, and that he's saying that, well, we should just call that everything's refracted up, raised up, he's going to say. But that, as I say, that then does mean there's a category missing in his looming thing. I mean, but as you say, below 0.14, there's a hole in there in his categories for what happens in that area, and he's going to have to.
And even then, it's purely a semantic argument anyway as to what you call it, which is kind of my point with Brian the other night as well. And
oh damn it! I had a really good point you were going to make about what you were saying there. Oh, no, I've just left my mind. Damn it! It was
about definitions.
Yes,
definitions dictating reality.
After money, it was something about the looming. Damn it! It was something about what you were. Why I was saying I would agree with you if you called it looming. Damn. Well, anyway, I've promised him that I won't call it looming anymore, and I'll use extreme refraction, extreme looming instead of. And yes, I mean basically, his looming is what we would call sort of extreme looming, or
or anything
greater looming, and then
utter looming.
Yes, and so he's left this hole now. What's he going to call things that are loomed less than standard looming? And I still haven't quite. I forgot the point I was going to make. I thought you might be interested. Damn it! Anyway, carry on. I've forgotten the point.
Well, I think Dean's been wanting to say something for a while.
Oh yeah, no. So there's something I noticed. I actually noticed with Glenn talking to Brian and Ranty a few times, and I've noticed it with you, Rumpus. And I don't think you address it in your document enough. Can you see my screen, Rumpus?
You can. Yep.
So the basic issue is, why do we lose this part of both of these objects? We'll call it M for missing. Why do we lose it? Now, flat earthers, I absolutely believe this, believe that light operates as a projection, and refraction only affects that projection. And by that, I mean, to get to the observer over on the left, that this is going to try and project this way, like so. But what they believe is, due to refraction, and when you're explaining it, and Ranty said this loads of times, what happens when that ray hits the ground? Ali B said it. Well, that ray's not going to get to you, it's going to hit the ground.
They say that often, yes.
Yeah, so the issue is, they're thinking it does that.
Correct.
What you need to show them is that
the ray starts going up high at the start. Yeah.
Yeah, that's what I tried to explain.
I've tried to do that about 10 times.
No. Yeah, but do it like this, Rumpus. Say your eye has a viewing plane, like so, and it's not a projection. It's this point here goes absolutely everywhere, as does this one. Now it doesn't matter. This ray is going to find its way to intersect this plane, and this is where you see it.
Yeah, I said that.
There will be a ray that meets your eye.
Yeah.
I said that about 10 times. I actually drew in a series of those rays, and I think about a week ago I had and I had to draw in about 6 or 7 rays to make the point exactly what we did. But he didn't accept it. I mean, I went on about this, and Brian, after Roohif had finished with him, made exactly the same point again, and I tried to draw in. I even copied the laser ray that I had in my tank, and they said, look, I can move this one end. If you say that's what it's like, I did showing you where the tangent met the surface. I said, look, I'll take this ray shape, and I can show you that I can always make it, if I don't have anything in the way, there's always a ray of that curvy shape that I can get from part of the object to your eye. I can always achieve that effect on a flat Earth. But he didn't seem to go, no, unless you have that, unless it's got to go straight, it's got to go horizontal. And if it doesn't go, if a horizontal ray doesn't get to you, then it's not going to get to you. Oh.
How about Chris Berry come in?
They really think there's only one ray that comes from each point.
Correct.
On anything. That's what they think.
That's what I say. I think they think it's a projection.
Yeah.
Because they keep going super looming hologram and all that kind of shit. No, it's light going in every single direction. Please learn what light is. You see the reflection in every direction. It only happens to be your viewing plane that you observe.
Well, I'd just like to point out, and the thing about a week ago when I had to draw all these lines in, Ranty asked me, so when I said there were more than one light ray coming from a particular spot on the object, he said, so how many are there then?
Oh my God.
This is the level of understanding they don't have. So I said billions. So you've got light rays going off in all directions. How the hell do you think we see an object from all angles?
If it was only question, actually, Rumpus.
One direction, you wouldn't be able to see it.
The other day when you were going through the, was it Gutierrez?
Yeah.
Yeah, and you said there is a way to determine which ray meets your eye from the object. And I always come at it from the perspective of a ray tracer where it's kind of reversed, where you draw a line from the observer to your object.
Yes, correct. Exactly right.
Is there a way using those Fermat calculations? Wow.
Yes. All right. It's wacky. It's amazing, isn't it? It's absolutely stunning. But it can.
I've been thinking about it for days. Like, how the hell do you do that?
It's amazing. It's amazing.
All right.
It's all to do with the have you heard of calculus of variations?
No.
Okay, that's what you need to go and read up on.
Okay, calculus of variations.
Correct. And if we perhaps we could have a hangout about it. I did a hangout about it with Philip about a year and a half ago, in which we discussed this briefly. But yes, if you perhaps we ought to have a hangout about it. I could go through it. Perhaps it's on the. Yeah,
I have to read about it first.
Yeah, indeed. Yeah. But just perhaps in principle. But given my problems I had with Hangouts today, I may never do one again. Try to. Sorry, Dean, you were saying you were explaining something.
Rumpus, can I have a yeah? I can't impress upon you more. I think that it's again. It's really, really interesting. It's really, really good to just look into all of this. But you are, by engaging with the flat Earth in this arena, you're just allowing them to fuck around, and.
Yeah, I mean, you're basically saying, why are we giving them extra publicity? Are we giving them extra credibility by bothering to talk to them? Yeah, that's a fine argument.
No, it's not.
Oh, it's not. No, okay, so that's not your argument.
No, that's not.
Sorry.
No. What I'm saying to you is that if you're trying to kind of tease apart observations at extremely low level when you've got fuck knows what.
No, I'm not.
Vertical density gradient. I mean, it's just.
But we're not.
No, it's completely pointless.
Yeah, but John, you seem to be confused about what we're trying to do. I'm not trying to model very random, turbulent sort of refractive conditions. I'm not trying to model those things. All we're doing here is invalidating their claim that image is a credible image to invalidate the Earth. Not only one, because they've got it wrong but two, the image is full of refractive wackiness, and I make that point. So it's an invalid thing to use.
Yeah, well, that's it. All you need to do is to say you've taken your observation under shit conditions, and it's swimming with refraction, and it's fucked. You can't make any determination or any kind of rational conclusion from that observation, and that's fucking it.
Yeah, but
what you need to do is take some like decent fucking observations above that kind of swimming refractive zone, like Miles Davis has. Extremely relevant, good observations,
Yes, but
Miles Davis has done.
But they were arguing quite correctly if that as Roohif pointed out, their argument is actually valid. In other words, if we were making the claim, let me finish.
Logically valid. There's a big distinction between valid and sound.
Yeah, if you're not familiar with this, it can seem a bit confusing. If you make for instance, if I made an argument for you that was logical, if I could take the premise, for instance, that pixie dust existed or something, and then I could make a great valid argument from that premise to prove that, I don't know, you got pixies in your bed or something. So the argument I could use subsequently could be what's called valid, but the premise is wrong, and so the overall argument is not sound, as it's called. But the actual internal logic of the argument could be valid, as it's called. But the overall argument relies on some premises, and if those premises are wrong, then the argument's said to be unsound, even though it's valid.
Yeah. So quantum erasers' argument is like, what is it? If the Earth is a globe, then you can't have a horizon greater than whatever the formula is.
Yeah.
The horizon is not greater than that distance, so that's premise 2, and then conclusion, therefore the Earth is flat, whatever, in its logical form. So he is following correct rules of logic. So Moden's Tollens is correct, and he's using second premise and combining that to get a conclusion. That is logically valid. But the first premise, so if the Earth is a globe, then the horizon cannot be further than this distance away, is false. So the argument is not sound. That's what validity and soundness, that's how they're distinguished. And an argument has to be valid and sound for it to be true.
Yeah, I'd just like to emphasize that again. So his argument is, first premise, globers are saying the geometric horizon is where the sky meets the ground. 2, there is a formula for saying where the geometric horizon is. 3, we have observations in which we can see where the sky meets the ground is not where the geometric horizon is. Therefore, the globe, the Earth cannot be a globe. But of course, laced in that was the first premise, that we are making the claim that the horizon is where the geometric globe meets the sky. But we're not making that claim. So the whole argument is unsound, even though logically, internally, it is a valid argument.
Yeah, it's logically consistent, but the first premise is false.
That's
so
correct.
The conclusion doesn't matter. Yeah. Chris Berry, are you coming in?
Well, we haven't invited him. Do you want?
I'd love to.
He said there's too many globers. I'm not sure he realises that was essentially what was going on here. Is it's not like an open panel or something like that. It's just
it's flatty bashing. Yes.
I'd like to chip in one thing about the low-level observations. Although it's technically true, it's not the best thing to go low. There is the other side to it, which is you can do it right. You know, you can account for those conditions. You can take observations on days when you know the temperature and pressure and you're going to get the best clarity and all that kind of stuff. And you can approach it the way Soundly did. You know, he had a spreadsheet filled with all the information for each day that he took his observations to keep track of it all and to be able to identify patterns, to know what was a good day to take an observation, what was a bad day, and so on. So he approached that the right way. The problem is you've got somebody like Travis who does it the complete opposite way. He keeps harping on about going out and doing observations for 18 months. All he's done is gone out and pointed a camera, not even learned how to use the camera properly, got fuzzy pictures, and done no analysis on anything about his environment the entire time.
Yeah, if you take some kind of account of the pressure gradient across your line of sight, you will get meaningful results.
Sorry, the pressure gradient between the observer and the target.
Yeah, that's what.
Yeah, there will be changes in that.
Yeah,
they're fairly small. But that doesn't really affect the gradient.
It's the vertical gradient that you're concerned about.
Correct.
Yeah.
George, and George hasn't said anything. George doesn't want Chris to come in. I was about to ask anybody if anybody wants to stop, doesn't want Chris in here, then I don't think we should let him in.
He said he can't anyway. So
well, that's great then. So George was. I think George was still trying to. George, I thought was going to try and say some. I don't know if whether George. We're stopping George from speaking here.
Are we?
I don't know. Well, he was.
No, I'm just listening and working.
Okay, you're happy, are you, George? I don't want to sort of.
Yeah, I'm fine.
Okay.
Well, I don't want to lose track of one point, and that is the other side of this argument, and I talked about it a little bit earlier, but there is no circumstance under which the horizon on a flat Earth could ever appear in front of an object. It cannot happen. That is absolutely impossible.
Yeah.
That's why I bring in swell and waves.
You can have some seriously wacky refractive situations where you've got a lump of cold air or something somewhere between you and an object, and it could be or hot air or something like that. Because
come on.
I mean, things like
it's incredibly contrived, though. Yeah.
Oh, absolutely. But something like a superior mirage.
You're going to have to go to some extreme lengths to find something like that happening. My point is simple. In the clear image, in the unrefracted image, that horizon is clearly in front of both of those platforms. That cannot possibly be true if the Earth is.
Yeah.
Now, that's the Modus Tollens argument that actually does work.
I think another way as well, looking at it from their side, my last video was about using, their claim against them about the perspective, horizon, and angular resolution. And the way it works out is for a 6-foot observer, your horizon works out to be about 3.25 miles away using this method, right? But if they want to claim that it's, you're seeing what you see because it's flat and there's a horizon, I mean, the fact that they think they can use the horizon in the first place is laughable to me, but that there's a horizon caused by perspective, they have to also admit that photograph is an anomaly, because on their model, they wouldn't be able to see 9 miles away using perspective.
That's got nothing to do with angular resolution, though.
That's one of the topics that Flurfers are thoroughly confused about.
I worked with it and showed how it all works out. It started off with 6 foot, and then I was specifically looking at plane footage, because that's the thing that really kind of kills it. It kind of grows kind of exponentially when you start raising the elevation. And for Jay Tolan's 28,000 foot observation, he should have been able to see 15,200 miles away to the horizon.
Jay Toll and I have come to a conclusion that he actually is lying. I think he's a Poe.
Actually, somebody commented on that on B-Ball's channel. Apparently that is the case, that he's actually been seen commenting saying he knows that it's a globe and he's just doing it for money.
Well, that's the thing about angular resolution. I honestly don't know anyone who knows more about the possibilities of angular resolution optically or photographically or telescopically than I do. I don't rub shoulders with anyone who knows more about it than I do. And I'm not saying that I'm the world expert. Obviously, I'm not. But I know an awful lot about it. And it is difficult for me to listen to the shit that is spouted by flat earthers on this subject, and in every aspect, I cannot express just how much it grips my shit.
It's one of the least understood by Flurfers. I mean, I asked, my favourite observation of like a missing mountain is Canigou. So the one from France over to Canigou, and there's like 2,500 meters missing, right? And I keep asking Flurfers, why is there 2,500 meters missing? And they go, angular resolution. And I'm like, do you realize there's a specific formula for this, like the diffraction limit formula? And when you plug in some realistic parameters into it, the diffraction limit works out to be something like 4 meters of unresolvability at the mountain. Like it's insignificant. It's nothing. But they just don't understand what they're talking about. They throw out buzzwords that they hear on Oakley and Quantum Eraser and have no fucking idea what it means.
But I'm actually building, as Rumpus knows, I think.
Yeah, your telescope thing was an amazing thing. Yeah.
Yeah. So I'm building an astrograph telescope at the moment, and I have been doing for a couple of years. I've just been gradually buying all the bits and doing the math to make sure it is tuned to within an inch of its life.
John, tell us about how it compares against the Hubble, your telescope, the diffraction limit on there.
The diffraction limit of my telescope. Well, the diffraction limit of the telescope in ultraviolet light is about. It will be about roughly 0.2 arc seconds.
Holy shit.
And Hubble commonly images in 0.1, 0.15.
That's amazing.
So, I mean, obviously, Hubble's it's an orbit.
Hubble's about 10 meters diameter, isn't it?
No. It's 2.4 meters.
Okay.
And my telescope's 0.356 meters.
Okay.
But the thing is, though, that Hubble, the time is money, and you've only got a certain amount of time that you can look at an object. But if I doggedly want to look at something, I'll just go and every chance I get, and I can build up data over and over and over and over again. So I'm actually quite, I wouldn't say an equal footing, but and I would look at things that Hubble wouldn't ever want to look at as well. So I mean, I can look at the moon, for example, in ultraviolet. So it's the things you can accomplish with a. I mean, it's a huge fucking telescope for an amateur, especially of a research grade. But anyway, don't make me bore you all to death with telescope nonsense.
Yeah, I'm very interested in your telescope and the way you've gathered your various bits and the way you ground your lenses and things is just incredible. Sorry, it's not lenses. Sorry, your reflective, your mirrors. Yes, to the amazing accuracy. Oh, that's right. You were how many? What was it? The accuracy on your mirrors. It was something amazing. It was how many? Some microns. Or what was it?
It's measured against the wavelength of visible light.
That was it. It was something incredible. That's right, against the wavelength of visible light. That was it.
So the aberrations in the surface of the mirror are measured against the wavelength of visible light. So the maximum, the mirror has a maximum deviation of 1/10 of the wavelength of visible light.
Jesus, I'd forgotten it was that. I thought it was I thought you were about to say something like 10 wavelengths of light, or 100 or something. But you're saying.
So it's a tenth of. Well, it's.
But
So if you're talking like 50,
isn't that sorry? But 1/10 the wavelength of light is not far off the size of an atom, isn't it?
No, it's nowhere near that. No.
Just trying to think there. It's 400 it's 400 nanometers. Okay, yeah, okay. So I suppose it's an angstrom. Okay, I suppose it's a factor of 100. Okay, all right, yeah.
Yeah, so you're say 5 or 600 nanometers.
Yeah,
it's so it's a tenth of that. So it's like 5 or 6, 50 or 60.
I keep on thinking that for some reason I keep on thinking wavelength of light is comparable. Not by a factor of 10 of an size of an atom, but yes, it isn't. That's why, of course, we can't use light to actually show pictures of atoms, and we have to use electrons or something because light its wavelength is so much greater than the size of an atom that actually prevents us from seeing the damn thing.
Yeah.
Yeah, the wavelength of light is 500 to 1,000 times larger than a hydrogen atom.
Yeah.
But the whole point of tuning this telescope as much as I possibly can, because it is achievable to get what you call a truly diffraction limited telescope.
Yeah.
So, which means that the image that you're going to get through that device is not limited by the telescope at all.
Yeah.
It's limited by the nature of light.
Yeah. But obviously, if you had a bigger aperture, you'd obviously be less limited. Obviously.
No, it's not. No, it's not. I mean, it's not a function of how big the telescope is. It's a function of how perfect the optics are, and I mean, it's a thing that's distinct to each device. It's not. It really. It's not. It's not. It doesn't. I mean, the thing with the reason why the reason why I can get close to Hubble resolution is because Hubble is not a diffraction limited telescope.
Yes. Presumably because you've got a smaller mirror, you can make it more accurate, whereas they've got a great stonking mirror, and it's very difficult for them to be as accurate as yours is.
Well, they fucked it.
I know they did, but yeah.
Yeah, so they didn't for complicated reasons. They didn't make the mirror the right shape, and they had to put specs on it, etc., etc. But it's operating quite a lower resolution than it could have. So it depends what you do.
You should one day, John. You should do a proper video. Do you do videos about you've done some videos walking around it, but I don't think you've done anything on the technical side, have you?
Well, I did a bit of a sort of kind of live stream of it, yeah. But yeah, I should, I suppose. Yeah. Anyway.
Yes. Anyway, before we get too telescopy,
we've gotten a bit off topic, I think.
Yeah. Well, I like your telescope chat. So I don't know if. So I must admit, because I've got rushed there, I may have lost. I don't know whether I've covered all the points that I actually wanted to make about this image. But I think we've pretty comprehensively said it's silly. Even the premise of the argument is silly, so that debunks it. But then we were trying to explain what is going on, and we've now established, in fact, after looking at it, that in fact the K value is actually not 1, and.
Don't forget, Rumpus. Scale and elevation. We've even compared it to the flat Earth, and it doesn't work.
Correct. Absolutely correct. Because, as we'll emphasise again, in that image, worth bringing up again, just in case people have missed it, if it was a flat Earth, then the legs here of the nearby platform, and the legs of the far platform and the horizon would all be in the same spot. And the fact that they're not means that the Earth is not flat. If you didn't have if you had no refraction and that was the case, that's what you would expect. Now, adding flat Earth and refraction together complicates things, but we also know, as Glenn and you said K isn't one, that would also be what if K was equal to 1. That was the circumstance you would appear to get. You would see the legs all entering the water at the same spot and the horizon would be in the same place if K was equal to 1. So we know also that K is not equal to 1 in this circumstance.
Correct.
So because the legs are there, that means I think it must be slightly less than. If it was more than 1, then.
Oh, please don't do this again.
If it was more than 1,
Glenn, stop it.
The horizon is above eye level.
If it was more than 1, then the one nearest to us would be.
Rumpus, do not make me draw a bloody diagram to explain this to you.
If it was more than 1, that would make the further thing. No, so I don't think it's quite 1. I'm going to now come down to.
Oh, God.
Oh my God!
The horizon is above the equivalent point on the platform.
Yes, so it's less than 1.
No, that's
greater than 1.
That's more than 1. Oh my God!
No, if it was greater than 1.
Oh my God!
If it was greater than 1, then the things further away.
Do you know? Wait a minute. Do you know when it's time for bed, Rumpus? Is when you are just wrong. That's when it's time for bed.
Well, that never happens, so I don't have to think that.
Rumpus.
I have to take that back. I did claim, though I must admit, not in one of my firm "this is correct" things. I just randomly said it could be close to 1, so I didn't actually firmly say. I thought it was about 1, so I didn't actually.
You said it's below
it could
1. Me and Roohif are saying it's over 1, and we know
I think
it's because of the laws of parallel lines, Rumpus.
No, I think if it's more than 1, then
Rumpus.
Oh my
God. It's John again. It was lovely to have a bit of a telescope chat with you, but if I was with you right now, I would boot you in the balls.
Yes, thank you, John.
Thanks, John.
So.
The image appears concave, right? Do you agree the image appears like a concave Earth?
He's not getting it, honestly. It really isn't.
No, it's not.
Go to bed, Rumpus.
If it was a concave Earth, then
draw a line of sight. How can I just best describe this?
I have had a very, very hard evening and a hard day as well. So I'm not. But I'm still. Oh, hold on. I have to think about this because
I'm going to draw it for you now. Give me 2 bastards. I was going to sleep, but now I'm pissed off with this. So give me a second. Oh my Christ! Stop sharing, Rumpus, and look at this.
Okay. I am very tired and shattered at the moment. I admit.
Yeah. The image appears concave. A is greater than 1.
All right. Okay. So what we've got here, Rumpus, is we've got the ocean surface. Yes. Can you see this?
Hold on. Sorry, I'm just. No, you're not sharing.
Oh, am I? Yeah, I am.
No, you are. You're on screen.
Yeah.
Oh, okay. Well, it's not coming up for me.
Click on. I'll tell you what. It's because you were sharing. I'll reshare again just for you because this is just for you because everybody else gets this. So.
Oops. Oh, bugger it. Okay.
Right, are you ready? You can see this now, yes?
I can, yeah.
Awesome. So I've got an observer over here. That's the green dude.
Yeah.
Now, we know that the green dude is a set height. We know that it's 1 meter. It's
well, don't worry about it. Put it on the ground. All this mess around with 1 meter is irrelevant.
No, it isn't.
It is.
This is what it isn't. And
utterly irrelevant.
Wait a minute. Are you sure it's irrelevant to the point, Rumpus?
Yes, I'm reasonably
would you bet your
sure.
correctness on that?
I must admit, I'm only working about 70% functionality at the moment.
Go balls deep in this,
it should make any difference to your point, whether you think it's...
Okay. So we've got this dude that is that high, thus I'm creating two parallel lines. Yeah. This red thing is the platform. It is intersecting at the same height that this dude is.
Yeah. What's a straight line?
On an infinite plane, where is the infinite plane going to converge to, given the laws of perspective and parallel lines? It's the black line, isn't it?
Yes, it'll converge on the black
Brilliant.
line, yeah.
So now we go out to the fucking far left platform. We go up from the base, the same elevation as the camera, and we have a look what's behind it, because it sure as hell should be the horizon, but it isn't.
Yes.
The horizon is higher.
That's my point. That's why I'm saying it's not one, because the everything's not in
Oh my
line.
God.
I said
Oh my
that
God.
5
But it's
minutes
greater
ago.
than
I
one.
went into this in
Oh my God.
5 minutes ago,
Oh
saying
my God.
because they were not in line, therefore K cannot equal to be 1.
It isn't. It's 1.1.
It's greater than 1.
Yeah.
Greater than 1.
Well,
There is, Rumpus, you can still see this. The only way for me to place this damn horizon here higher than that black line is for an inverse value of your, well, a greater value than K, K equals 1.
Well, that's
Because at
that's the
1.1,
you just described a negative K
this.
value there.
No.
Sorry, that line that Dean drew is kind of misleading. That's
The
not an
curved
upwardly
one
reflecting
he's just
line.
drawn is a negative K value.
That's an error. Yeah.
Yeah.
Right.
Okay, so look at this. We've got this. In order for this point here to appear higher than this point here, when we are here, what do we need? We need a negative value.
That's a positive. That's a positive value you just drawn.
Sorry,
Oh, yeah,
sorry, I'm getting it wrong. Yeah, so 1.1. K equals
This is a
1.1.
shit fight.
Yeah.
Fucking hell.
You're making much more of a mess of this than I did, Dean.
No. I know what I'm saying. 1.1.
Well, you're the only one who does.
It's a higher.
Have a put it this way.
value.
So K equals 0 gives you a geometric view of the Earth.
Straight line is K is equal to 0.
Straight line.
K is equal to 1 follows the curvature of the Earth. And if it's bigger than 1, then it's smaller than the curvature of the Earth.
It's tighter. The ray curvature is tighter than the curvature of the Earth.
Same thing.
Yeah, which would make it look concave, right? And eye level. And the horizon would be above eye level.
Oh my God, you got
Yeah,
there.
correct. I've always
Got it? Okay.
There. Oh my God, Rumpus, you made it.
But
You made it.
I've stated that all along.
No.
You said K was less than 1.
No, but it depends what you talk about eye level. You see, you've got this thing about you're only presuming.
When we say eye level, we meant creating a parallel line in relation to the surface of the water with the elevation of the observer or the camera. That was it. With that simple survey data, you can tell that it's either concave Earth or it's a K value greater than 1.
Yes, actually, perhaps I might agree with you. Actually,
Oh my God! How long did that take?
well,
To bedtime,
you were so busy dealing with all the errors you were making, Dean. It was.
Oh my God! Stop trying to deflect now, Rumpus. The errors I were making is
It's so
because
easy.
I was actually thinking about my bending deformer that I had on my in Maya. That's why I was.
If I said go and have a Bex and a lay down, would that mean anything to anyone?
Yeah, I do need to lie down. That's for sure.
Yeah, Bex. There used to be a product here in Australia called Bex, and it was just like codeine, and it used to be like an afternoon.
Oh, I thought you were talking about
thing
the beer.
for-
It's Beck's beer. I thought you were referring to Beck's beer.
It's a codeine that used to be around in the 80s or something, and like housewives used to have like a Bex and a lay down. They used to advertise it as a Bex and a lay down in the afternoon, and it would just fucking put people to sleep because it was like how much, 30 milligrams of codeine or something.
Holy shit! Did it get people addicted?
Yeah, it was addictive. Yeah,
Yeah.
Oh, wow.
but yeah, you need to go to bed, Rumpus.
Yes, I do.
Just one last question. So, have you now changed your position, Rumpus? The K value in that picture is above 1. Yes.
I think actually yes. I think.
Excellent.
Awesome.
Yeah.
Awesome.
That'll do then. What do we do now? It's almost midday here. Any flurfers want to come in? Chris Berry doesn't. Ranty said no because it's too late.
It's a guy who goes on until 3 o'clock in the morning.
Valid.
Just for Rumpus to just think about something when he's going off to sleep is, I would strongly say to you, give up this this big fight about what swimming refraction is.
Swimming refraction?
Oh, sorry.
Yes.
Can I jump in?
Well, just
swimming refraction. What are you talking about?
Well, just arguing with flairfers about what can be seen, what can't be seen.
You seem to be confused.
It seems like you're trying to interrupt me.
Well,
I can't have
you've made the same point 5 times now, and I've invalidated 5 times.
No, you haven't. No, you haven't.
I have.
No, you haven't. It's not 5 times. It's 3 times.
Well, it seems like 5.
But I can't stress enough. Just you're making an arena. You're. I mean, this is where they want to be, and arguing with them about it is just it's a hiding to nothing. What you need to encourage them to do is actually get off the fucking away from water level and actually make some fucking decent observations. You'll never win this argument. Ever. Never. Ever. Ever.
Well, we are, because again, I don't understand your point. They have made a claim about this image, and we have just invalidated it on several fronts. I don't understand where you're having a problem.
But
you seem to be very confused about what's going on.
You think I'm confused?
Yes, I think you are confused. You don't seem to be understanding what we're doing. We're not proposing. You seem to be saying at one point I was proposing that we suggest observations from like this can be, I don't know, evaluated accurately so you can do things with them. But what we can do is invalidate them. And no one, as I've I've never suggested that getting down close to the water is a good way of doing observations, or that's something that we should be processing. But we can invalidate such things, but we don't need to account for everything wacky that goes on in them, because all these strange refraction effects you're going to get. And you seem to be very confused about this.
I'm not confused at all. I mean, I mean, obviously, you know my background. I mean, anything, approaching sort of, I don't know, sort of 10, 15 degrees towards the horizon. You're
yes,
just not.
Yeah, astronomers don't like anything below 15. Absolutely, yes.
Yeah. So I mean, you're just not going to derive anything of any meaningful value.
We can invalidate things. You can invalidate things quite happily.
It just seems to me that you're kind of going round in circles with these fuckers.
No, we're not. This is the first time we've done a hangout on this, and this is the first time we've had a sort of get together dealing with this claim, and we've invalidated the claim. Blue Marble's done an excellent video on invalidating himself, and Miles has done one as well. But there's been a little bit of confusion even then amongst some people about where horizon is and what's bending by what, and we've sort of tackled some of it here, and separately we've tackled it. But
it just seems to me that there's sort of a huge amount of effort is going into actually arguing the toss about what you can see, what you can't see in this area.
I understand your point of view. I think I'm not interested in anything below 15 degrees, but we do live in a world where you have to deal with those sorts of angles quite a lot, and surveyors have to do it. But I know for you're always busy doing things at 15 degrees or above. But that's because you're in a specialised field. You can avoid having to deal with reality down at 15 degrees or below. But surveyors and the rest of us do have to deal with it down there. Now, when it gets down to this sort of angle, it gets really, really, really silly. But you can do stuff in between silly levels, like 1 foot or something, and up to 10 degrees.
Well, that's not strictly true, because you can actually. My main gripe is that all you need to do, to make long distance observations at a low elevation, as in a low angle elevation is get up to a decent altitude.
Yes, no one's disputing this.
And that I would be much more. I wouldn't be having any gripe at all if your kind of argument was, Christ, get away from this swimming refraction area.
I do say that. So that
and get up.
You've got to invalidate what's presented to you, John. We can't just ignore it. We have to make the counter argument and point out this is flawed in several regards. One, about the position they don't understand that the geometric horizon, that in normal standard refraction, which does exist, you do get a difference between the apparent horizon and the geometric horizon, which is an issue that hasn't really been fully elaborated upon. And there are several other issues.
They're not listening to you.
Well, they're never going to listen to me. They're never going to agree. But that's not the point. There are people who listen to them, perhaps, who might be affected, and there's our own personal discussion and educational, where, for instance...
Well, I don't know if they're listening to you either.
Sorry?
I don't know if they're listening to you either.
Okay, I don't give a toss who's listening to me. How about that, John? You can go away being happy about that. But the point is, I'm learning stuff, and other people are learning stuff about this, and if you're not interested, then fine, go away. Don't.
I think. Wait,
all right, ding.
Yeah. I think. I want George to come in a second because we wanted to explain something. But just really quickly on this, I think the issue that we've got. I agree with John. Partially, I agree with Rumpus partially, but the issue is. Long distance observations of the magnitude that you talk about, where refraction is so insignificant, are actually harder to come by than walking down to the beach, and that's an issue that you're always going to have with primitive individuals that don't really want to, that just are looking for confirmation bias, and that's the issue. Go on, George.
Can I just say something? Sorry, George. Sorry.
Go ahead. I'm cooling my heels.
Be quick.
We've got the plain truth, Travis. He's just spent how many days? 17 days or something? Sitting next to a beach, just swinging a camera around. How much did that cost?
We don't care.
All that time.
We don't care.
He could have gone and got to some elevation and made some really startling observations.
Yeah, but he's not going to do
that. Some really good stuff.
Yeah, we tell him. This is what I tell him whenever I encounter him. Going down there and trying and draw conclusions from Larry. I mean, I'm showing on screen. I don't know whether I'm showing at the moment. This some of the images he got. But yes, that's his problem, and I tell him repeatedly, if you get down there, you're going to get into trouble. I don't know what you. I do not think I understand what point you think you're making, because it's not a very good one.
No, John. Just really quickly, I've actually spoken to Travis before, and I've said that exact same thing, and I've said all you're doing is taking photos of amazing distortions and recording refraction, which is amazing, which is brilliant, but that is the only place he finds flat Earth or some tiny aspect of flat Earth. If he did it your way, he wouldn't, and he's scared of that, and I'm sure they all are.
That's exactly right.
That's it.
All right, George.
Go for it, George.
Sorry, George.
No problem. I'm just rather amused listening to it all. John, something you need to understand, you're taking this stuff really much too seriously. I mean, Flat Earth is a joke. A lot of these hangouts and discords, like Jose's, Globebusters, Nathan, Sean G, all these are kind of social clubs. If you look at all these different shows, you have about the same 200 to 300 people showing up on all the shows. And these guys have staggered their shows. Was it Arwen starts early in the morning before Nathan, then Jose comes on, and the others come on, and there's some people out there that have no life, and they just watch show after show after show, and this is more like a social club than anything. I mean, there's nothing serious. You don't take any of this stuff seriously.
You got to remember, George, that I'm Scottish. It's maybe a
What's that got to do with it?
To Scottish people, even jokes are serious, George. It's just that
simple.
simple.
I see. Okay. but a lot of the, it's kind of like morning coffee, where all the business guys get together or whatever to start their day off, and that's how I kind of see a lot of this is going. Is nobody takes this stuff seriously, at least on the globe side. Well, some people do, but you really don't. You shouldn't. It's just a joke, something to occupy your time.
Well, I think that's lots of positive. I mean, just trying to counter the arguments offered. I mean, it is encroaching, flat earth stuff is encroaching into the public discourse and putting
there's some of that, but I mean... Go ahead.
Right, thanks. And I think refuting it is useful. But also, I mean, George and I, for instance, George has done some wonderful experiments. He's been found educational, and so have I. Just learning about things like this calculus of variations and how light behaves, etc., has been very educational for me and finding interesting things from that. So it can have a positive effect, just in terms of one's own understanding of reality, and also dealing with idiots. Who are making silly arguments and how to counter them with better arguments and how to deal with a malicious debater who's determined to attempt to bring you down and try and trap you was one of the reasons I got involved in this was deliberately putting myself in a position where I had to deal with Nathan, where I was at a disadvantage to someone else who was making a counterpoint because I believe I might be able to find those skills useful in other areas of life, was another useful thing to me. So there are several skills that one can acquire by getting involved in this in terms of education and just general life skills.
Just to clarify my position, I've said this so many times. I really don't care what people think the shape of the Earth is. I don't care. But I see the flat Earth movement as one small facet of this general kind of anti-science, anti-mainstream movement, which I think is absolutely what I think is absolutely correct to rock against as much as possible. It's bigger than the flat Earth.
Yes, normally these flat earthers tend to be also conspiratards as well. So this is why when you seem to be getting upset about the fact that we're invalidating a stupid argument, you seem to think that we're doing something wrong. No, we're not. We're invalidating a stupid argument that we don't want to be adopted by other people, and we've got to put a counter to that. We're not getting involved in suggesting people to make observations from low down. No one has ever done such a thing. So we're just countering some silly arguments, that's all.
Well, you didn't describe... You didn't describe my argument there, Rumpus.
Well, I don't think you know what argument you're making, I'm afraid. You seem to be quite incoherent.
Guys, you're going round in circles here, and it's really getting ridiculous, to be honest. Can we move on?
Yeah.
A while back, before all this kicked off, I think Roohif was asking George to speak about the difference between the pressure and temperature gradient with regards to refraction, so maybe George can have a wee talk about that. If he wants.
That's fine. I can if you're ready.
Yeah, go for it.
All right. Tell you what, give me a minute here first. I need to take care of Con again here. Con's having a lot of problems these days. I'll be with you, George. I'll be with you in a minute.
Well, at the risk of kicking off the same conversation again, I'll chip in a little bit. It's just to say, in general, if you're doing any kind of so-called debunking of flat Earth, then you're dealing with what they're putting out to show why it's wrong. So there's no point telling somebody who's on the globe Earth side what's right and what's wrong with regard to observation and things like that, because it's not up to what we're doing. It's what they're putting out, and then you're going for that to show why it's wrong, so that the people who will learn from it can see. If you don't have a counter argument for all the nonsense, then the nonsense gets to prevail.
Someone's hammering their keyboard like crazy.
Yeah.
Sorry.
Yeah.
That's a bit of high frequency trading there, was it, Glenn?
No, but I'm actually going back to work soon.
All right, indeed. I'm going to go to bed as well. I say I'm utterly shattered here. So,
to be quite honest, John, the sensible thing for all of us to do is just to laugh at these silly fools and forget about it.
Yeah, the only trouble is there are sort of susceptible people, like, for instance, Jose Gonzalez, who picked up these silly memes and things. So I think you do have to challenge them. It would be nice just to ignore them and hope they get smaller, but they are influencing other people and certainly attracting a sort of conspiratard sort of collection. And we've seen from the way that the memes that QE generates that they are being spread around.
Yeah. Now I'm coming to the conclusion, though, that the ones that are influencing may not be worth trying to salvage in the first place.
You might be right, yeah. But I think there must be a spectrum there somewhere between someone's a lost cause and then the middle. Whatever, where there's a boundary there somewhere. There must be a boundary there somewhere where there's those people beyond the ones who obviously just pick up the memes eagerly, and then there are those other ones. I mean, for instance, there was a guy that Conspiracy Cats got round to thinking, because he picked up the flat Earth memes, and then he became a flatty, and then Conspiracy Cats made a big effort to talk to him. Same with Jose Gonzalez. I mean, he picked up the flat Earth meme, and then as a result of interactions with people like me and others, he gave it up. So there are these people who are affected by the memes, and you can do something about it. But I agree.
There's been a few, and you don't always see them on YouTube as well. Sometimes they'll email or send messages on Twitter and stuff like that. So.
Yeah, or they're just quiet. You don't know what they're getting up to. There's that hidden audience that's just sitting there watching stuff, and it's just the noisy ones that you're dealing with, like the QEs and the Nathans, but those are obviously a lost cause. They believe what they want to believe, so they're going to count. Right. Particularly in Nathan's case, they're making money. So they're lost cause, but there are people they're influencing, and there are people that you can counter influence now. You know, you can regard it as a lot. Well, not what's the way of wasting your time, but as I say, there's been other benefits. Like for me personally, I got involved in the sort of the adversarial debate deliberately to hone skills that I might find useful in other arenas, and also I found that it's very educational. It forced me to, brush up on my calculus and God knows what else.
And you don't ever really know who's watching.
Correct.
Like an example I can give from experience a few years ago is when I used to frequent IMDb's message boards a lot, and I was on there for a couple of years, and I received a message to one of my posts one day from somebody who is what they call a lurker, and he had been watching and reading everything that me and the others in that kind of particular board had been saying for over 2 years, and that was the first time he ever felt compelled to say something. So
are you a film buff then, Al?
Yeah.
Oh, right. What did he say?
I don't remember that. He was just responding to a post I made, and he, for whatever reason, something I said kind of compelled him to have his say, But, there's a lot of people like that. That's the point, that they just hang back in the background and they watch and they take the information in, and they don't necessarily do what we do. You know what I mean? They don't get involved in panels, they don't leave comments.
And exactly, those are the people in the middle there. Those are the ones you're going to affect. They're going to keep quiet. They're not going to be the Nathans that are shouting at you. They're going to be the people in the middle who could be affected, and they're necessarily not feeling confident about which way they're going to go. And those are the ones that can be influenced. And necessarily, they're also going to be the ones that are going to be quiet.
Yeah.
Okay, George is back. Go, George.
Just a quickie, just before. Al, have you seen 2017 yet?
No more quickies.
Sorry, 1917. Honestly.
I was going to say.
Sorry, you can see what state I'm in. 1917.
No, I haven't seen it
Let
yet.
George speak, then I can go and do what I need to do today.
I have.
Oh, right. Okay. Was it good?
Yeah.
Go for it, George.
Oh, okay. Well, it's been rather interesting. The question was being asked about a comment I guess I made on Ranty's show the other day. And I can deal with that without talking about lapse rates and all this other stuff that will be way over most people's heads. Most of us are familiar with the Kidder equation, the CIDDOR. If you go to the engineer's toolbox on the internet, there's a very good discussion dealing with refraction. and different equations. There's 3 equations that they deal with on there. There's a Kidder equation, there's the Edling equation, and there's a quick and dirty equation that is simplified called the shop floor equation. And the Kidder equation, of course, is very involved. It's very accurate, but there's an awful lot of computations that need to be made in order to use a Kidder equation. You have to essentially use the calculators that are online in that particular toolbox. Or Wolfram Alpha also uses the same equation. You can get refractive indexes from in Wolfram Alpha using the Kidder equation. But there's so many parameters in intermediate calculations you have to go through. It's basically unwieldy and impossible to use with one of these online calculators. To try to program it yourself on a handheld calculator is just ridiculous. There's a simpler equation called the Edling equation, which is quite accurate. Not as accurate as the Kidder equation, and it has restrictions that are not as general as on the Kidder equation. But both the Kidder equation and the Edling equation, there's 4 parameters that you input. There's temperature, pressure,
humidity and CO2.
Yeah, humidity and vapor pressure of water. And the Edling equation is a lot simpler to use, and you can actually calculate it by hand. And it agrees within about 5/100ths of a part per million with the Kidder equation, as long as your temperature is right around 20 degrees centigrade, and your pressures don't differ much from 90 kilopascals to 120 or 110 kilopascals. But most of the time, it's within about 1.5 parts per million over a wider range. Now, there's an equation that I use quite a bit that I find is reasonably accurate, and that's this shop floor equation, and it does not use vapor pressure like the Kidder or the Edling equation. You have 3 parameters: temperature, pressure, and relative humidity. Now, the comment that I made is if you look at any of these equations, the primary driving factor in affecting the index of refraction of light is temperature, because temperature directly affects the density of the air. Humidity.
So does pressure, though, right?
Well, I'm getting to that.
Okay. I kind of need to do an intro as to what the question was. Ranty is saying, well, I forget whether it was Ranty or someone else, but they're trying to imply that the normal direction of refraction is upwardly refracting rays, so an inverted density gradient to what we normally see. And my point is that the normal state of affairs, where you've got your normal pressure gradient and you've got a normal temperature gradient of 6.5 degrees per kilometre, will result in a normal downwardly refracting gradient.
Yes.
And for the gradient to be inverted, so you have upwardly refracting rays, the temperature gradient needs to be something like 34 degrees per kilometre, which is huge. Therefore, the pressure gradient is dominant over the temperature gradient. Do you agree with that?
To some extent. just let me finish here a second. Is I want to clarify this thing about the pressure. Is if you look at any of these equations, the index of refraction is a strong function of temperature changes. And it's also a fairly strong function of temperature or pressure changes. But the thing is how do you define a small change in temperature versus a small change in pressure?
Well, the pressure gradient's quite steady, whereas the temperature gradient can change a lot. So we've got to compare the steady pressure gradient against the standard. You would
keep interrupting.
Standard lapse rate. Sorry, you go.
The thing is look at relative pressure densities in terms of or pressure changes in terms of inches of mercury. Extreme ends on your barometric scale on a barometer is between 28 inches and 31 inches. So you're looking at 3 inches of mercury change, and that's quite a bit. And when I've played with these equations, I've investigated them extensively, and if you're you can have let's see, your index of refraction will change on the order of about 1/100th of your temperature differential. I've been working on that. I found some rather interesting things out in dealing with changes in both temperature and relative humidity, and with pressure changes, barometric pressure changes. And you can really simplify these equations, it turns out, if you look at differences rather than absolutes. And I'm going to eventually publish something on that, because I have never seen anything related to this. And this discovery that I made, I think, is rather important. Now, there's a lot of games you can play mathematically to simplify a lot of these equations with approximations. And the degree with which you need to use the Kidder equation is if you're looking at real minute differences in temperature, like if you're looking at really small gradients going across boundary layers, like on the order of 1/10 of a degree. If you're upwards of about a degree or so, you don't have to really use the Kidder equation. The other equations are perfectly fine and will give you the same values, unless you're looking for really, really small changes, like on the order of parts per million or tenths of a part per million, which you have to do if you're looking at tenths of a degree changes. Your index of refraction changes on the order of parts per million and tenths of a part per million. Now, the pressure is a strong driver for index of refraction. And if you look at inches of mercury, the difference in inches of mercury divided by about around 10 gives you your index of refraction changes on the order of 1/10 of a part per million. Well, I won't get into it because this is going to pass over everybody. But
yeah,
the thing
I
is,
think I can simplify the question, though.
Yeah.
Can I simplify the question?
Sure.
What temperature lapse rate will cause an inverted density gradient, like upward refraction?
I haven't looked at the lapse rate to do that. All I look at are temperature differences and barometric pressure differences. I could back calculate to get what the lapse rate is for that.
Yeah.
But
that's what I've done, and it's about 34 degrees per kilometre, which is obviously 5 or 6 times greater than the lapse rate in the standard atmosphere.
Okay, so you want to know for the inverted so that the light bends upward rather than downward.
Yes.
Okay.
Yeah.
Well, I'll look at that. I can't give you that number offhand right now.
Yeah. No, that's what I've done with the SIDOR or KIDOR equations is, work out the pressure and temperature at the surface, and then, get the pressure at 1 kilometre up and work out what temperature that implies for no density gradient. So the index of refraction is the same. And it's about
the interesting thing is, if you look at Snell's law, and as your angle of incidence starts getting parallel to the boundary interface, you get strong bending as you go across the interface. Rumpus could show you a picture that I did with a laser where I took a laser pointer and I almost got it really parallel to the surface of the lake. And when you're off to the side, you see this thing really taking a dive down. It's about 40 degrees or so off the horizontal that it dives down when you're parallel. So what's happening, and I played with it earlier today, if you shoot a ray of light or like a laser beam parallel to the horizontal, to the surface of the earth, or even if it goes through, which is essentially a uniform density, like say you have a layering going on, you shoot into one layer. Well, the thing is, we never have perfect layers where it's perfectly homogeneously and perfectly mixed. And the laser beam, even though it is shooting horizontally, will bend downward. And Snell's law shows you that. All you have to do is take your incident angle at 90 degrees. Well, not incident. Not 90 degrees into the boundary, but parallel to the boundary. So in in the equation, you have the incident angle being 90, or the theta angle being 90 degrees, which they measure from. Typically in the Snell's equation, it's written where you measure the angle with respect to an orthogonal angle, an orthogonal to the surface. So when that angle is 90 degrees, you're parallel to the surface. And when you're parallel to the surface, you can calculate, even for very, very minute temperature differences, the beam, the angle of the light going through the interface will bend downward, even though it's perfect. The beam is launched perfectly horizontal with the earth. And this is something that a lot of people don't understand. They think a laser beam or a ray of light will go horizontally forever in a uniform volume of air. And it doesn't, because of the fact that there's a gradient, a slight gradient because of gravity. And the light beam will bend downward. And Snell's law shows you that indeed does happen.
Is that calm barking?
Say what?
Is that calm? Someone's got a dog barking in the background. Is that calm?
Yeah, he's outside barking at deer. Yeah, the deer are bedding in the woods here. Go ahead.
No, I was just wondering, your conversation there, is that Roohif?
Yes.
Actually, I've got something you might be interested in here. I've just closed my thing about showing you the gradients that give you different effects, actually, so that you might find interesting. Really, if I'm just going to load up my thing again.
Yeah. So, I want to know the temperature lapse rate that causes an inverted density gradient. Yes.
That's exactly what I've got here. If you just give me a chance to boot this up again. Well, actually, in saying that, I haven't got something quite specific, but I can show you. I haven't actually got an actual answer for it. Yes, actually, I might have overplayed that. But I think
I can bring up the Sidor equations. Is it Sidor or Kidor? Like, how do we know how to pronounce his name?
I'm not sure how you.
I think it's Sidor, isn't it?
I thought Sidor. Yeah.
No.
I've got his equations. Like, there's a dude that like translated his equations into Python, and I can run that and basically demonstrate what I'm trying to demonstrate.
Well, I've got the equations programmed into my handheld calculator if you need something.
I'd like to know if the Rumpus is calmed down enough so that
very calm.
we're friends again.
Well, let's point out, John, you started off saying you were going to kick me in the balls and things early on in this conversation without me barely saying a thing. So,
when have you ever barely said a thing, Rumpus? Be honest now.
Well, our interaction with you, I had barely said anything. Anyway,
I think you. I mean, surely you must realise that sometimes you need a bit of a kick in the balls.
No. Do you understand? You sometimes need a kick in the balls. How would you like me to come and kick you in the balls? Anyway, I'd just like to show this. George, my God, the noise. I just want to show this to before I fall off my chair in my state of half. This is. Can you see this, Glenn? Is he fallen asleep or something?
No, just on mute.
All right, okay. Yeah, so this is, I got some information here. You basically just using that equation, actually, this one here, the one that gives you the curvature, this, where's it gone? This stupid, this one here that you're familiar with, which gives you the K value, which is effectively what you're asking.
That's the Edlin equation, I think, isn't it?
I don't think that's called the Edlin equation. Really?
Possibly. Not entirely sure.
I didn't think that was the case. I mean, if it is, because I didn't realise if it's got a name, I didn't realise it had a name. If it does, I'll be very, because I'm in the process of trying to derive this actually from first principles.
Good luck. But if you read Sidor's paper, you'll probably be able to do it and derive the Sidor equations.
I do have the Sidors. I think I do have Sidor stuff, but anyway, just using that equation, which gives you the K value, which I think is what you're interested in. You end up with these little things here about the temperature, because you and there's a paper that also actually someone's monitoring the K values of using some theodolites and using there's a scientific paper that goes into just here that I've got. Actually, they measure the different the K values that they experience.
Oh yeah, it's like between -4 and +16, right?
That's right, you've got it. Okay, you've right. Yeah. Okay, I won't bore you with the thing again then. But that's a great paper, absolutely fantastic. George, you're making an incredible amount of noise. Anyway, so just using that. Okay, so if you're familiar with that equation, then I'm probably not telling you anything you don't know here. Just giving you some temperature gradients that give you. This gives you no no looming, no refraction. Gives you, in other words, so that's -1 gradient of so -1 degree from ground. So if you take ground level as 0, because we're just doing gradients.
Yeah, there you go. That's exactly at top left, that yellow line.
Yeah.
So dt dh.
Yeah.
So change in temperature per change in height for everyone at home. 34 degrees per kilometre will give you a K of 0. So the K of 0 equals no refraction.
Right, okay, here we go. Right,
exactly,
Okay, so there you are. Yes, indeed. So
that is the number.
Great. Okay. Well, glad to be in a service. So yes, that in other words, so that's the temperature gradient you require for generate no refraction. This is the gradient that gives you the circular rays that I was talking about, and the K is equal to 1. And then George has actually experienced in the things he's done, and which we were just describing about, more than one for the thing that I was having difficulty absorbing. He was getting DT of H of 0.7K, which would give you more than. And this is the one here I put in the value, which you indeed the quote exactly well remembered, Roohif. This plus 16 value they quote in that paper.
Yeah, which is huge.
And it is just unbelievable, isn't it? Like super curvy. And though, of course, when we say super curvy, of course, you must remember that curving to match the curvature of the Earth is not very curvy at all. In fact, just remember that in scale. Because of course, although I've been drawing those curvy things, when you actually extend it, to curve the Earth, you wouldn't be able to see a curve over 50 kilometers. You would not be able to visually discern that there's a curve going on if you're looking across the curve. And so,
anyway, that is my point at the top left. You require a temperature gradient of 34 degrees per kilometer, which is obviously 5 or 6 times greater than the lapse or the DTDH in the actual atmosphere, which is 6.5 degrees per kilometer.
Which is this one here.
Therefore,
this standard one.
Therefore, the pressure is dominant over the temperature.
So what do you mean? It's this temperature thing it's this temperature grade that leads to the pressure.
No.
Well, the pressure at any particular height. Well, the way
they are interrelated. Yes, pressure and temperature are interrelated. Obviously,
I think the pressure is a function of temperature.
They are interrelated.
Not directly.
Yeah,
exactly. They're not. Yeah, not linear.
No, they're not linear. No.
Yeah, if you constrain the temperature, but you change the pressure to be, the pressure at 1 kilometer, you'll get obviously a downwardly refracting rays of light. If you have to adjust the temperature by 34 degrees to get a K of 0 to have no refraction.
Right.
Okay, and that is that DTDH up in the top left.
Yeah.
And my point is that is obviously greater than the normal temperature lapse rate.
Yes.
That's why I say pressure dominates temperature.
I suppose, what do you think about cause and effect? I think, because obviously the atmosphere is a hydrostatic. Sorry?
Yes, they do affect each other, yeah.
Yeah, I mean, for instance, the way we did our ray tracing, we worked out if we knew the temperature. No, I suppose, I suppose it's. Well, you could argue what's cause and effect here. You see,
I know what you're getting at.
Yeah, because I mean, the question, yes, what causes what? I mean, obviously, when you do the if you try and work out, for instance, what the density is at a particular height, you can work it out if you know what the temperature is. But then you might argue, I suppose, if you know what the pressure is, then you've got to have a particular temperature. So the question is, what's cause and effect here?
It's kind of what you plug into the equation. Like I know that they kind of bounce off each other, the temperature and the pressure.
But definitely you can definitely work out one. If you make one unknown, you can work out the other one, and the pressure will then cause that. But the question is, but normally what happens? So, for instance. Normally, if you just think of a standard atmosphere in a uniform, then along comes the sun and warms something up, and it changes the temperature gradient, and then that causes a change in pressure and gives you things like inferior. So I would argue that the temperature is the driving force here. The temperature gradient is the driving force here, not the pressure.
Yeah, it will change the pressure gradient. Yeah.
Yes. Okay. Great.
Okay.
Okay. But the DTH. Because the way you work out the refractive index is you work out what the density is. To work out what the density is, you usually take the temperature, and then you work out what the temperature gradient is, and from that, knowing the hydrostatic equilibrium that exists, you can therefore work out what the density is at somewhere else, and from the pressure.
You can't say that. You can't say that the temperature is the driving force.
I can. I just
did. Yeah, you said that. Yeah, which doesn't make it true.
It is true, though.
Which one is stronger? How big does the temperature gradient need to be to overtake the pressure gradient?
But I believe the pressure gradient to be a function of the temperature gradient, though. That's one.
Yes, it is. And that complicates things.
You know, a really important thing to remember is what actually drives refraction, which is density.
Yes, absolutely.
Right.
Anyway, I've made my point.
The thing is, guys, the point you're missing here is you really can't compare the gradients of temperature to pressure. They're apples and oranges. I mean, you have to define a figure of merit as far as what you. How can you say one overtakes the other?
Yeah, I'm a bit confused by that statement. Yeah. I mean, although there might be one greater than the other one,
how are you going to normalize it to compare? You know, there are two different types of entities. You can't really say a temperature gradient or a pressure gradient overtakes one or the other. I mean, they're different units. You can't compare them.
Yeah, I know, but one gradient, so the temperature gradient in the standard atmosphere is not enough to cause an upwardly refracting ray.
But it causes a change in pressure, though, I think.
I understand, yes.
So therefore,
but not enough.
So in other words, I believe that the change in temperature causes the change in pressure, which then causes the change in density, which then causes the change in refractive index.
No.
Anyway, I got to go. It's like 20 to 1.
Roohif, before you go, there was a thing I wanted to talk to you about. Are you going to have to split?
Yeah, message me on Skype now, and I'll chat about it later.
Okay.
I was trying to leave like 45 minutes ago. Mm-hmm. So, all right.
Yeah. All right. Bye, Glenn.
Message me on Skype. All right. See you soon.
Great stuff.
You can evaluate this very easily. Earlier today, I figured out an equation for green light at 532 nanometers. The equations that are in this. So
say again. How many?
532. The standard green wavelength.
Right, yep.
Okay, because the equations given for the shop floors for 633 nanometers red light, helium neon laser. Now I'll give you the numbers here, and this equation will tell you the direct relationship on pressure and temperature. Now, there's a slight correction that needs to be made when you enter in relative humidity, but if you ignore that, the difference, the index of refraction is 1 plus a correction factor, or 1 plus some delta, okay? And the delta is 7.9112 times 10 to the minus 7th times pressure divided by 273.15 plus temperature in Celsius, and the pressure is in pascals.
Mm-hmm.
So if you want to argue which is the dominant, that equation will tell you. And like I say, it's hard to compare the two because, what do you consider a small pressure change? As barometric pressures can go between 28 and 31 inches of mercury. And your temperatures, say, in the atmosphere can go anywhere from minus 40 degrees C on up to, say, 50, 60 degrees centigrade in the troposphere. So, I mean, I'm not exactly sure what's being asked here, because Rumpus is right. These equations kind of hide the fact that temperature change, it's incorporated in the equation, the effects of temperature. Temperature changes the density of the air. Pressure also, densities related to the pressure. So, they're all interrelated. So I'm not sure how you're going to, parse this thing out. Now, of course, all you have to do is go back to Snell's law, is that if you go from a medium of lower index of refraction to a higher index of refraction, the light will bend, excuse me, the light will bend away from the interface more. That if you go in at a certain angle of incidence with respect to the horizontal, the light will come out and be refracted to an angle that's away from the horizontal. And so all you have to do is look at your indexes of refraction. I mean, it'll go the other way if you go from an area of higher density into lower density, and that's all you have to look at.
I think the important thing, if we are going to look at this in relation to for instance, the plain truth premise. I mean this is.
Well, I guess I'm not fully understanding. What is the question that wants to be answered here?
I think the question that wants to be answered is is how to define the effects of refraction in relation to the whatever observations the flat Earth wants to try and
that's a non-starter. But that's a non-starter to begin with, because everything that I see that the flat earthers present are pretty much in unstable atmospheric conditions. So you really can't assess anything. And plus, they never give you any data as far as what temperature measurements are in the optical corridor. So you're just taking a best guess at things, taking a wild-ass stab at it.
Well, that's we're pissing in the same latrine, George.
Exactly. And that's why I don't get involved with trying to evaluate these photographs, is because it's nonsense.
Yes. Yeah.
But George, we're trying to invalidate a claim based on these photographs.
But the thing is, you can't conclude anything from these.
You can conclude they're wrong.
Well, yes, of course.
Well, there we go then. So the job done.
Yeah.
Yeah, I know you don't like hearing this, Rumpus, but what the fuck are you doing? Spending so much time arguing the toss over exactly what's happening in just absolutely swimming refraction.
I'm not. You keep on saying I am, but I'm not.
That's what you've been doing.
The same piece
That's what you've been doing.
No, I haven't.
John.
No, I haven't.
We've been over this enough times. Don't start going down that road again.
I'm sorry.
Are you drunk or something? You sound drunk.
Scottish, I'm always drunk.
Right, so you are. I thought you were drunk. Right, that would account for it. Stupid twat. go and sober up and go back to Sean G's hangouts where you've got real idiocy on display.
Sorry?
Go back to Sean G's hangouts where you've got some really intelligent conversation there to deal with.
Sorry, can you say that again?
Oh, shut up. No, I'm not going to say it again. I'm going to go to bed. I can't stand any more of this idiocy. So anyway, thanks very much, Al, for saving the day there. And thanks very much for doing that.
No problem. I was available, so.
Yeah, thanks, Al. That was great. And right here, well, I'm going to go to bed.
Just tell me when he's fucked off.
Yeah, one of these, maybe in another week or so, once I work some more on this, I have some really good stuff for you, Rumpus, on this, on these equations and refraction, some of the things that I've become aware of that I wasn't in the past. It's there's some really interesting relationships that I've come across.
I think he's gone.
Oh, okay.
So who else is left? Who's here?
I've been paying attention more to the chat, so it looks like pretty much everybody's away. It's just us three, so I think that's probably a good time to wrap up.
Is it? I thought I heard Big Blue.
He's away as well. I'm going to stop the YouTube stream anyway. I think we've outplayed this one enough, and everybody's leaving. So, yeah. Just before I do that, I'll just say so everybody can hear. Thanks to everybody for coming and watching me host the Rumpus's presentation, and no doubt we'll see each other on all the different channels somewhere.
Well,
anyway,